Everyone. Welcome to day 2 of GIAN course on adsorption techniques for carbon dioxide capture, modeling and simulation insights. So today we have 3 lectures and 1 tutorial. A tutorial will be in the afternoon. Morning we will have 3 lectures. Now the lecture 5 will start on fundamental of adsorption process, where Dr. Ravi will cover the thermodynamics and also the diffusion and kinetics. Okay, that is followed by lecture 7 of Dr. Debanshu Stuck. He will be introducing differential algebraic equations, and we'll have this tutorial on basics of MATLAB and also the Aspen software according to the schedule. Okay, Dr. Ravi, you can continue. Thank you.
Okay. Good morning, everyone. So today we will start with thermodynamics. So these are the topics we will be covering in next 2 hours. So it's kind of like, especially we start with thermodynamics of adsorption, and then we talk about heat of adsorption and how we can compute the heat of adsorption through simulations or through experimentation and so on and so forth. So we'll talk about like what insights we can get from the heats of adsorption. So next one we kind of like go into the kinetics part, so which is like diffusion in porous media, right? So we kind of like talk about Knudsen diffusion, viscous flow, surface flow, how to compute the diffusion coefficients, especially in terms of simulations. We don't go into the experimental techniques to compute the diffusion. This is because there are several techniques, so it depends on system to system and how you measure and so on and so forth. So the explanation is also so complex, so that's why we are not going into it. And then we kind of like going through the breakthrough measurements, how we can do breakthrough measurements, how we can measure breakthrough things via experiments, and what we can get from breakthrough experiments. Last one is like kinetics, right? So the kinetic models we have, when we kind of have the data, how we can fit using the models we got, and what kind of information we get out of it. Okay, so these are the 4 topics which we will cover in next 2 hours. Okay, so why we have to study the thermodynamics, right? So look at these ones one by one. So what thermodynamics will give what thermodynamics will give is the following, right? So the first one is, right, what is the amount of solute that can be adsorbed on a surface, right? And then second one is what state variables like temperature, pressure or any other variables that affects this adsorption process. If it affects the adsorption process, how it affects it, positively it affects or negatively it affects, and how we can maximize the adsorption by playing with temperature or pressure or any other state variables. Okay. So the third one is how can we determine the stationary and maximum adsorbed amount. So stationary means at any given pressure, maximum means at max how much it can adsorb, right? So this information we can get through thermodynamics. So last one is, and very important one is, if the gas adsorption is happening, where exactly it is happening, right? What is the location? Whether it is happening to a specific functional group, or it is happening near the pore surface, or it is happening in the bulk. So where exactly it is happening, how we can actually recognize it. Okay. So this is because once we know where exactly the process is happening, like say for example a functional group, kind of like when we introduce a functional group, it kind of adsorbs the gas molecules. Then we know that this adsorption is happening near the functional group, we can add more functional groups. So for example some groups are not good, so then we kind of like create defects by removing those and then increase the adsorption. So that is why we kind of like have to have an understanding of like where exactly this adsorption is happening. And then the next one is how much energy is required to remove these things. Once the adsorption is happened, right? So to kind of like continue with the process, we have to remove this one. So that means desorption should happen. So if desorption should happen, then how much energy we have to give it to it. So that information is also we get from the thermodynamics. Okay. So let's go one by one, right? So that is the fundamental equation which we all know. The delta G is Gibbs free energy, and then delta H is the enthalpy, T is the temperature in Kelvin, so this is always a positive number, delta S is the entropy, which are all change in entropies, right? So So any process to happen, so what is the fundamental thing it has to follow is that the change in Gibbs free energy should be less than 0, then only the process will happen. That's what we kind of call instantaneous process, right? Okay. So when you look at that equation, we know that delta G is a negative number here. If adsorption has to happen, then this delta G should be negative, then only it will happen. At equilibrium, delta G is 0. Okay. Okay. So that's one first one. So next we will go one by one. So we leave about delta H. So go with T. T is a temperature which is in Kelvin. So it's always a positive number. Third one is delta S, which is entropy, change in entropy. So what is entropy? In simple words, what is entropy? Entropy talks about the randomness. So if we don't go into the fundamentals and all, in basic, entropy talks about the randomness. So what is happening in the gas adsorption? We have a surface here, and then we have gas molecules, right? So these gas molecules will come. So this is kind of like, say, initial configuration, and then these gas molecules will come and adsorb on the surface, right? So when you look at the S initial, that is entropy in the initial state of the gas molecules, which is in the gas state. So the randomness in the gas state is very high. So this is a very big number, right? And what about this final one? So these gas molecules will come and adsorb onto the site. So they kind of like stick to the surface. So the randomness decreases. So this is a small number compared to this one. So therefore delta S, small minus big, always less than 0, right? So now look at this equation. So what we have is delta H is equivalent to delta G plus T times delta S. We said that delta G is a negative number. So this is negative, this anyhow leave it, and this is negative. So the overall everything is negative. So delta H is always negative. What it means is that whenever adsorption happens, heat releases. Okay? So that's why adsorption is an exothermic process. It releases heat. So at equilibrium, what happens at equilibrium? Delta G is 0, right? So your delta H will become T times delta S. This is the equilibrium condition. Right. So that's what we kind of like showed, that change in enthalpy is always negative, and therefore adsorption is an exothermic process. Right. So as we said, heat always releases. So what is the challenge with heat release is that yesterday we kind of like have discussed that when the temperature increases, adsorption decreases, right? That we discussed in terms of Le Chatelier principle, right? Now what we are saying is that we have a solid surface and a gas molecule comes and adsorbs and heat releases. So what happens to this heat? It has to dissipate, right? So some amount of heat will So when a gas molecule comes and sit onto the surface, so the heat releases. That's what we kind of like discuss. And this heat will be absorbed by the solid, maybe part of it, and part will be dissipated to the surroundings. right? So we never know what happens. So it may be like all the heat will be kind of like dissipated to the surroundings, or all heat may be kind of like absorbed by the solid, or it may be partly divided between these two. So whenever it kind of like goes everything into the surroundings, we don't have any problem. But the challenge comes in the other way around, when all the heat releases is absorbed by the solid. So the temperature of the solid increases. So it is not good for the adsorption. So the desorption starts, right? So that's why we have to have like always look into the adsorption and the heat of adsorption, because if the heat of adsorption is pretty high, so it actually favors the desorption. Okay. So that's why we every time what we do is we kind of like try to calculate the heat of adsorption and see it is very high or very low, right? So and then what we can kind of like inference from the heat of adsorption, that's what we will do, right? So you can see, read it. So adsorption is the exothermic process, and therefore energy is released during this process of adsorption. That's all good. Measurement of the heat of adsorption of the specific gas onto material is then very important consideration, and it actually gives knowledge of the surface area and porosity of the material. So why it is that if you have more surface area, it can absorb more gas molecules. If it absorbs more gas molecules, it will release more heat, right? So based on the heat of adsorption from the process, we can understand the surface area and the porosity of the material, right? So that's why this is also like one way to look into it. Okay. So then the third one, heat of adsorption, is also indicates the measure of strength of interaction between the gas and the solid. So if the gas and solid interacts really well, so it releases more heat, right? So delta H talks about the strength of the interaction. If the interaction is very less, it releases less. So even that also kind of like gives one information. So in all, the heat of adsorption is a fundamental thermodynamic feature, and its value can be utilized practically when developing and assessing the material. So that is the reason why we kind of like try to extract the heat of adsorption. So there are several ways, like there are several definitions of heats of adsorption, like differential heat of adsorption, isosteric heats of adsorption, enthalpy of adsorption, and so on and so forth. But we fundamentally don't go into everything. We will only focus on isosteric heat of adsorption. Oh yeah, okay. Before going to that, you can see some of the materials, right? So here what we have is the list of materials like zeolites, MOFs, and silica gel. What we see is that what is the heat of adsorption. So typically for zeolites, the heat of adsorption is pretty high. So when the heat of adsorption is very high, the problem is that heat or the temperature. So that's why it's kind of like a very hard. So MOFs, so moderate, so we kind of like tunable for efficient cycling. So that means that when adsorption happens, we have to desorb it and then again restart the process. So in that sake, MOFs are good. It will have more cycling efficiency. And then silica gel has a very low heat of adsorption. So it's easy for desorption, therefore good for cooling. Okay, let's go. So among all the heats of adsorption, specifically we focus on isosteric heat of adsorption. So this is also called differential enthalpy of adsorption. This is because it actually talks about the change in enthalpy of adsorbate when we add a small amount of gas molecules into the system, right? So this is the definition how we get it. It's ratio of infinitesimal change in the adsorbate enthalpy, that means the solid enthalpy, to the infinitesimal change in the amount adsorbed. Like when we have a solid, so some gas molecules are already adsorbed, so which has an enthalpy of some H, and then you add like a small amount of gas molecules, then calculate the H2. So what we get is what is the change in enthalpy when we add small amount of this one, right? It goes here. Okay. So similarly, higher the isosteric heat of adsorption, it means stronger interaction between the adsorbate and adsorbent, leading to higher adsorption capacity, but harder for the desorption, which we already discussed. And then lower isosteric heat of adsorption means weaker interactions, making desorption easier, but reducing adsorption capacity. So we try to kind of like have to manage these two things. So the isosteric heat of adsorption cannot be like higher or cannot be lower. So we kind of like always have to play around with these values. Okay. So like what usually we observe, like we will not observe like same for all the cases, but in general cases how we observe like isosteric heat of adsorption. So in homogeneous adsorbents, right? So isosteric heats of adsorption remains constant at low loading, right? That means that at very low pressures, isosteric heat of adsorption is kind of like constant with respect to the loading, and then it kind of like increases, right? So with increase in the loading. So that means that isosteric heat of adsorption is not same with at all loadings. That means that low loading means that, so how do you calculate the isosteric heat of adsorption? Say for example, we have only one gas molecule adsorbed onto the surface, right? So that is our H1. Then you add one more molecule, calculate H2, and then this delta H will give you at low loading. But the same measurement can be done at high loading. That means that in the initial stage itself you have like hundreds of molecules, right? So that is our new H1. Now you try to add one more molecule here. So then calculate H2. So this will give you new delta H. So that means isosteric heat of adsorption depends on the loading. Okay. That is for homogeneous. Usually whenever we have a homogeneous surfaces, this kind of behavior we observe. This will be something like this. Say if we plot, so this is isosteric heat of adsorption and this is with the loading. So usually at low loadings it is constant, and then so it may increase something like this. So that is for homogeneous surface, that's what we say. And a different behavior is observed for heterogeneous adsorbents. That means that the surface characteristics of the adsorbent is heterogeneous, right? So that time isosteric heats of adsorption decreases with the loading, and it's kind of like goes something like this. Okay. So at the end of the day, the point I would like to highlight is that isosteric heat of adsorption does not kind of like follow a same trend in all the materials. It depends on the material to material and gas to gas. So it may kind of like constant, increase or decrease. Okay. So that is the only point you have to learn here. Good. How we kind of like measure it, right? So experimentally we can do by two ways. One is kind of like from calorimetric measurements, like you add the adsorption, like you add like few amounts of gas molecule and see the increase in temperature and then calculate back. Otherwise we can actually calculate from the adsorption isotherms, right? What we have to do here is that, I think I have somewhere. So we will use Clapeyron equation. So that's the Clapeyron equation. So we can use the Clapeyron equation to compute it. So what we have there is isosteric heat of adsorption is equivalent to RT square dou ln P over dou T at any given loading Q, right? So this we can write it as R maybe. Right. So because here we have T square dou T, so that I can write it as dou of 1 over T. So 1 over T is like minus T square, so this comes here. So it's like minus something. So what we can do is that at any given loading, right? This is at given loading. So first we try to extract the adsorption isotherms, which is the function of pressure versus the amount adsorbed Q at different temperatures. Say for example, this is at one temperature T1, this is another temperature T2, sorry, it all should start from here, okay, and it is at another temperature T3. So first we have to do is that we kind of like try to extract the adsorption isotherms. What we need is that change in pressure with respect to change in temperature at any given loading. So that means that first you fix the loading. So any loading you take, okay, and then so read the say P1, P2, P3. So at any given loading Q, what we have is P1 versus T1, P2 versus T2, P3 versus T3. So we have these data points. What we can do is that we can actually plot 1 over T versus logarithm of P. So they must follow a straight line like this. Like so, because we have 3 points here, so just like put it here, somewhere here, connect it. What we want is dou ln P over dou T. That means that's the slope of this one, and multiply with R, we'll get the isosteric heat of adsorption. So this is another way without going for calorimetric measurements. When we have the isotherm data, we can do this one. Okay. Yeah. So this is the one you can see. So what here you have in addition to this one is that, right, you have at different Qs. So that means that this corresponds to one Q here, as you see. So similarly at another Q, and then you can actually plot it. You can see that in this case all are like parallel. That means the slopes are same. So that means that isosteric heats of adsorption is constant with respect to the loading. Okay. So how we will do same thing from the simulations, right? So we kind of like use the fluctuation formula. So what you see here is that the brackets here kind of like talks about the ensemble average. We kind of like, it means that we take like different ensembles, that means that different configurations of the same structure, and then calculate the, so this N is the number of molecules in the system. That means when you are trying to do the gas adsorption, you try to insert a molecule, then try to count how many molecules are there in the system. U is the total potential energy of the system, and then so only 2 terms are there, and kT is the K is Boltzmann constant and T is the temperature, right? So like this, through GCMC simulations we can calculate the isosteric heat of adsorption, right? So look at this one. This is the example, right? So what we see here in the yellow one is with the Clashes-Clapeyron equation. That means from the experiments what they have done is they calculated the adsorption isotherms and try to get the isosteric heat of adsorption. And then here 295, 300 and 305 at different temperatures, the isosteric heats of adsorptions were calculated using the fluctuation formula from the simulations. So you can see they are all very well in line. So this is heat of adsorption in 1 geolite, which we kind of like discussed, which is around 40 kilojoules per mole. Okay. And what else? Yeah. So this is isosteric heats of adsorption in different MOFs, which is calculated using simulations again, right? You can see one interesting thing here. This is CO2 adsorption in different geolites. So the first one you can all see that on the left hand side what we have is the adsorption isotherm. So these adsorption isotherms in 3 different MOFs have 3 different characteristics. You can see this one, the one in green and then one in red, like which is GIF8 and MOF74. They follow Langmuir kind of adsorption isotherms. That means type 1 adsorption isotherms. You can see clearly. But however, if you see the MOF5, which is in the blue, it follows type 2 kind of adsorption isotherm, right? It's kind of like going and then going. So here it's like monolayer adsorption is happening, here multi-layer adsorption is happening. And with respect to the adsorption characteristics, you can see that in these two cases, right? So like especially in the red one and the green one, like you see the amount adsorbed is pretty low, but it's always increasing. A slight increase, I cannot say, but especially when you see the third one for MOF5, it's like a sharp increase is observed. So even you say like all three are MOFs, but you can see three different characteristics here. Here in the first case, isosteric hits of adsorption is almost constant at 30. In the second case, it's kind of like going from 17 to 25, and in third case, 15 to 30. So again, as we kind of like discussed, isosteric hits of adsorption depends on the system as well as the type of the gas molecules. Okay. But it is very interesting to kind of like extract all this data from the simulations, especially this course is for like based on the simulations. Even before we go for the experiments, we try to run the simulations and see the isosteric heat of adsorption and then understand whether this actually makes sense or not before synthesizing any material. Okay. However, as we kind of like also discussed, the force fields is a challenge. So we have to kind of like validate the force field before going for these kind of calculations. So these are very simple calculations anyone can do on any system. You can try using GCMC whenever you got the time. Okay. So these are all do with the isosteric heats of adsorption. So the second one we talk about the diffusion, right? So far we kind of like talk about the isotherms, thermodynamics, how to extract the isotherms, what information we can get out of the isotherms, and so on and so forth. That means everything to do with the equilibria. So the second one, which we also important in the adsorption, is the kinetics, right? So maybe we can say that. So you can try to kind of like do all the adsorption equilibrium things, and then say that okay, this material is good for the adsorption. So, but if we don't kind of like consider the kinetics, so how it will affect? So that's what we will see now, right? Why the kinetics is important. So that's what we kind of like discuss in this part. So whenever you see the practical solids in the industries, they are porous, and then overall adsorption rate depends, especially it's kind of like controlled by the diffusion inside the particles, right? That means that even it can accommodate more number of molecules, even it can adsorb strongly, but the thing is that if the diffusion is slow, it will take long time to reach the equilibrium. So then the adsorption becomes very slow process. Most of the time it will be the rate limiting step. Adsorption is like usually a spontaneous process. So it happens very quickly. As we discussed, whenever we have a pore structure like this, so here if the molecule is diffusing pretty slow, then it will take long time to reach the end of this one, right? So it slowly happens. So then what happens is that when you try to kind of like get time versus adsorption data, it happens very slowly. Happens like that. So that means that to run an adsorption process, you need a very long time, right? So that's why even equilibria is important. The equally important thing is the kinetics, right? So how the diffusion process occurs inside and so on and so forth, that's what we will look into it. Even before going to that, like, so the pore surfaces and all is more complex. Before going to that, we kind of like, let's see first what kind of like diffusion occurs in a cylindrical capillary. So that means that we are not considering any pores, we just consider a diffusion is happening in a cylindrical pore. So something like this. So assuming we have a cylindrical pore like this, and a gas diffusion is happening through this. So as simple as this one. So these are the several mechanisms that can happen, right? So what is Knudsen diffusion? So that means that, okay, so it's kind of like it can go through like all these things. So one is Knudsen diffusion, which we will kind of like discuss one by one, then viscous flow, then continuum diffusion, and then surface diffusion. So the gas molecules can go from here to here using any of these 4 mechanisms. Okay, so we'll see what these mechanisms actually contribute. We'll see, come back this one later. So this is the Knudsen diffusion, right? So Knudsen diffusion kind of like happens when the gas solid collisions are important. That means that when the gas molecule that enters is kind of like colliding with the wall, going back. Right? So that's what Knudsen or free molecule flow is, where the gas molecules collide more frequently with the walls of the container rather than colliding with themselves, like with other gas molecules. Okay? So here the gas composition is not important because gas-gas collisions are not important. What is important is the gas-solid collisions. Okay? So this usually happens at very low pressures. That means when we have very low number of gas molecules, these gas molecules will try to go and then collide with the solid walls, and then the diffusion happens. Okay? So to happen, the driving force for this process is still concentration gradient only. So why the gas molecule will go from here to here? Because of the concentration gradient. Because of the concentration gradient, it wants to go from here to here, but while going for that, it actually going through Knudsen diffusion. Okay? So here what we kind of like characterize this one by Knudsen diffusivity. So we calculate the Knudsen diffusivity, and then we kind of like see this. And from this process, what can happen is that because the solid wall collisions are very important, so the separation can happen. That means that some molecules may collide with the wall more number of times compared to the other molecules. So they can actually, like, some molecules may move faster, some may move slower. So then the separation can happen through Knudsen diffusion. Okay. Okay. So we kind of like talked about the cylindrical pore. But what about our geolites or MOFs? They don't have cylindrical pores, they have different pores. So what happens there, right? So that is a complex process, because usually we cannot characterize the pores of a geolite or MOF, like how exactly it looks like. But what we kind of like can see is that what can happen when a molecule collides with the wall, right? So for example, here we have a solid surface, and then a molecule will come and then collide with the wall. It can go in any direction. Sorry. Right? So this is called diffusive reflection. That means that for all these things, it has equal probability. We never know where it will go. Okay? But however, when the surface is pretty smooth, like what you see in a carbon nanotube, right? Carbon nanotube is kind of like almost close to the perfect surface, right? So then what happens is that most likely the gas molecule which kind of like collides with the wall will reflect back with the same angle of incidence. Say for example, it comes with an angle theta, it will also go with theta. If it comes with velocity vi or momentum, whatever, it also leave with the same velocity. It will not lose the velocity, it will not change the direction. So the angle of incidence is equivalent to angle of reflection, and then velocity will be conserved or momentum will be conserved, right? So that's why whenever we see the diffusion in carbon nanotubes, they are like 2 to 3 orders more than compared to geolites or MOFs or so on and so forth. What you see in carbon nanotubes, the diffusivities are in the order of 10 power 4 or 10 power minus 3 meter per second. But when you see geolites or MOFs, it all depends upon 10 power 6 to 8. Anyhow, that's still questionable, but yeah. So they are in the order of 10 power minus 6 to minus 8. This is because this is the reason. So the collisions in a smooth tube is most likely to be a specular collision. So it comes like that, what you can see there. But whenever we see a geolite which has a structure like this, which is like not, surface is not uniform, right? So where it hits the wall matters. Say for example, it hits the wall here, it will come back most likely. If it hits the wall somewhere here, it will go back like this. So the pore characteristics is very important to understand the diffusion in geolites. So that's why the pore surface we have to analyze before understanding the gas diffusion in geolites and MOFs. Okay. Right. So the second mechanism is viscous flow. So this is nothing to do with anything. This is just because of the pressure gradient. So it will act same on all the molecules, right? It's just like flow is happening. All the molecules will flow with the flow. So we don't have any control on this one. So the driving force here is the total pressure gradient actually. And how we characterize this one is the viscosity. Only viscosity matters when the pressure, because the pressure gradient is same. The viscous fluids will go slower, like slightly less viscous fluids will go faster. So the only parameter that characterizes the viscous flow is the viscosity. Okay. So here no separation will happen because all the species will go with the same flow. Okay. So the next one, which is very important one, is the continuum diffusion, right? So the continuum diffusion is actually kind of like opposite to what we kind of learned in the Knudsen diffusion. Knudsen diffusion is when gas molecules are colliding with the solid, whereas the continuum diffusion is happening between the collisions between different species. That means that it's still pores only. You have, this is gas 1 and we have gas 2, right? So we are trying to separate these two gases. So then, right, you have G1, you have G1. I wish we have one more. All are black only. Okay. So the continuum diffusion is characterized by the collision between gases of different types, not of the same type. Okay. So this usually happens at higher loadings, because at higher loadings we have more number of gas molecules. So they try to collide with each other rather than colliding with the walls. Okay. So different species move relative to each other, and then binary diffusion coefficient is the one which we kind of like characterize. So when we write the fixed equation, which is the flux, which we write like this. That is the flux, and then J2 is the flux of the second component, which is characterized by diffusion coefficient of 2, 1. It is density by dou J. So here the binary diffusion coefficients will come into picture. So we have like so many formulations like Maxwell-Stephan formulation, Lagrangian formulation, and so on and so forth, but because we are not dealing mixtures in this course, so we are not talking about that framework. And discussing these frameworks itself is 1 hour lecture, so we don't kind of like go into this, but just remember this is the fixed equation. So that's the flux is equivalent to d12 dou c1 over dou z. That's the flux of the second component, which is going d21 minus dou c22, and this d12 d21 is called binary diffusion coefficients, which dij, which is, and the factors that affect here is the total pressure, loading means loading of the molecules, and the temperature, right? So higher the temperature, it will have higher energy, so it will most likely collide with other gas molecules most frequently. So similarly the pressure, when the pressure is higher, so it will try to be close with each other and then collide with each other. Nice. So the last one is the surface diffusion, which is more complicated and very important to understand in terms of the adsorption. So this happens inside, but not like Knudsen diffusion. So there are several mechanisms that people have been proposed, but we usually go with 1 or 2. So the first one, usually we kind of like talk about only one now because of the time one. So once the gas molecules enters into the pore, right? So this is assume like a geolite pore. The gas molecule adsorbed at one site, and it want to go to the second site, which is here. So in Knudsen diffusion, what happens? The molecule will come and collide with the walls and go like this, right? So in surface diffusion, what happens is that it will not go like this. It will just jump from one side to the another side like this, right? So what it will do, it will first sit here, and it will wait until it get the energy that kind of like required to jump from here to here, and then jump from here to here, jump from here to here. So this is what we call it as surface diffusion, because the diffusion is just happening on the surface from one side to the another side. Oops. I think something. Yeah.
Sir, what force is bending the path of that molecule?
No. This one we like. You mean to say how it is going like this? Why not like this? That's what. No. This is kind of like what we are saying is in terms of the activation barriers, right? So, for example, when we try to get the free energy profiles, right, on the surface, what is usually here is, so here it will have very low free energy, that's right, and then it's the free energy kind of like very high, so it will not like go in this path. So it's kind of like go to a free energy where it is more like, so that's kind of like corresponding to the barrier kind of stuff. So it prefers to go to a place where it has to kind of like it experiences low resistance and then go back to again to the adsorption site. So that's the free energy related stuff. Yeah. Right. So in the overall thing, we kind of like have different stuffs like diffusion barriers, like what happens in a system, assuming this is kind of like a pore there. So right, so here we have the pores, right? So generally, because of the chemical potential gradient, the gas is moving from one side to the other side. Then we kind of like try to understand what kind of barriers can exist. So the first thing is that on the feed side, so the gas molecules are like moving in the gas side. So there will be an external resistance that like gas molecules have to move, and that will be like you can ignore it. So usually gas molecules experience very low resistance, and that's why the diffusions are very high. So the second one is that when the gas molecules try to enter onto the surface, right? So you have a pore here, right? Something like this you have there. So the gas molecules, the reservoir is here. So that means you are sending gas molecules. So gas molecules are coming. It's not that all the gas molecules will come and enter into the system directly. Some gas molecules will come and hit at the surface. So then it will try to kind of like move on the surface like this or like this until it enters into the system. So this one we call it as surface barriers. That means that the gas molecules that has to experience some resistance to enter into the system. It is not same for all the molecules. Say for example, this molecule may be lucky molecule will kindly directly enter into here and it does not experience any surface barrier. So this may be a poor one, so it go and hit here and then it will kind of like roam around. Sometimes it may go back here and come back and do whatever it wants and then enter into the system, right? So the extra path it has to travel. So that kind of like we also need to consider the resistance there. That's what the resistance we kind of like to see. Once it enters into the system, like somewhere here, so then it has to kind of like diffuse through it, right, from one place to another place. So this is either we call it as surface diffusion or like depends on the kind of diffusion it happens. It's also called intracrystalline diffusion. That means within the crystalline thing it diffuses. So it's called intracrystalline diffusion. And then it has to dissolve, right, if I want to go back. So therefore these gas molecules have to kind of like experiences these many resistance before reaching the end of the pore. Okay? So this is an ideal case, right? Whatever we are talking is an ideal case. That means that okay, there is a surface here, even whenever we say it has a pore network something like this, but still it's an ideal case. That means that whenever we say like okay, this is my energy landscape, so that means ideal things are there. But when you kind of like try to synthesize a material, it will have a lot of defects, right? So these defects will again affect this diffusion process. So look at those ones. So whenever we kind of like try to see, there will be so many structural defects. That means that, so maybe you have a pore like this, say something like this, while synthesizing the crystal like a geolite crystal, right, a defect formed in such a way that some of the pore is closed, right? So when we kind of like try to compute all the diffusivities, everything based on the ideal structures, what you will get is the ideal case. But in reality what may have is that, so there may be defect at the entrance, there may be defect in between, and then you see whenever we kind of like considered sometimes what here they considered is that these gas molecules kind of like, see there is a defect there. So the gas molecules cannot go there, it enters, because it cannot travel, it has to come back and go, right? So these are all the extra resistances it has to kind of like experience because of the defects inside. So there can be grain boundaries, because when we have like more grains, so the boundaries can create a lot of defects. Intergrowth can be one kind of like defect. And then surface barriers, what you can see here is that, I will not go through everything, but what you can see here is that the gas molecules that enter into the system, here you see at the surface, the forces experienced by the gas molecule is very different. Say for example, so you consider two gas molecules, one is exactly at the center of the crystal, so it experiences forces from all the directions because it has, right, something like this. But what about the one molecule that is exactly at the entrance? So one side it has the crystal, another side it has all the gas bulk reservoir. So the forces that is acting from this side is quite different from this side, right? So this molecule behaves differently than this molecule. So those are the things which we kind of like have to consider whenever we kind of like try to model things. Because when we kind of like model using simulation softwares, what we do is ideal case. That means that we kind of like consider everything else is perfect, but which is not the case. That's why whenever we kind of like try to compare the experimental data with the simulations, we kind of like most of the times we may not able to match it, and we kind of like question the force fields and others, so on and so forth. But at the same time we also have to consider that there will be so many defects and so many other factors that actually influence the simulation results. And usually in experimentation, what people do is that they don't care, because of the fact that what they are seeing is the actual one, right? So when they kind of like try to synthesize a material and try to prepare a membrane, they say like, okay, this is my membrane, and then they will just run an experiment and try to see how it is performing. But they will never kind of like thought like, okay, what exactly happening inside, so why it kind of like changed like this, why it kind of changed like that. They don't care, because that is an actual thing. But when we kind of like try to model it, right, because we are not doing the actual one, we are trying to mimic the actual one, so we also have to consider everything like this into the system, right? And yeah, so these are something similar like this. This is an extreme case where you kind of like see a gas molecule adsorb and travel till the end, and where it found that all the pores are blocked at the end, right? You see the gas molecule enters from here, it kind of like put all the efforts to come here, but it wants to dissolve, but this pore is blocked. So this is one kind of like situation, like people kind of like try to model and see how it kind of affects the diffusion, because these molecules have to travel additional path to locate the pore which is open, right? So what people has done is this, right? So they kind of like first try to compare, like first perform the experimentation, get the diffusivities, and then perform the simulations in two experiments. One end is no defect at all, another end is like full 100% is like fully blocked, and then try to get the diffusivities in both the cases, and then they kind of like try to see how much percentage of pores are blocked in experimental setup. It's kind of like you go back and see. Okay, oh my god, we are running late, but so these are the diffusivities that we try to compute from simulations. The first one is self diffusivity, right? What we try to do in self diffusivity is that say you have a pore this, and then you have like 10 molecules which is diffusing through this pore. We kind of like tag each molecule with one number, right? So then try to compute the mean square diffusement of each particle. So that means that with respect to time, how much the first particle traveled, how much second particle traveled, how much third, fourth, fifth, and then, right? So you calculate the mean square displacement. That means that, so Ri of t minus Ri of 0. That means from time t is equivalent to 0 to time is equivalent to t, how much it traveled squared. So that is mean square displacement. Okay. So we kind of like try to get at time 0. So we kind of like get 1, 2, 3, how many? 5 particles are there. So we try to kind of like get the mean square displacement of each particle. This is x, this is y, like x1, x2, x3, x4, x5. So this is mean square displacement of particle 1, this is mean square displacement of particle 2, like that. And then at the end what we do is the average of all these things. So that's the average of x1, x2, x3, x4, x5. Like that we try to at time 0 this much, 1, 2, 3, 4, 5, like that. We get all these things and get the average and try to plot time versus mean square displacement plot, which is like this. So we have time on the x-axis. So this is average mean square displacement. It does not correspond to any particle. It is average of all the particles in the system. For long time, if you run a simulation like this, it will be a straight line. So which the slope, right? So from the slope, you can get right, 6 times, right? 6 times d, right? So from this we can calculate the self diffusivity. So this is one way to calculate the diffusivity. The second one is the corrected diffusivity. Here what we will do is we will not kind of like monitor each molecule, but we will try to monitor the center of mass of all the molecules together. So it's kind of like 1, 2, 3, 4, 5. Then we kind of like center of mass somewhere here, and then after some time maybe center of mass is here, after some time center of mass is here. So calculate the center of mass of this one with respect to the time. So we have only one, so that we kind of like try to plot it, which will give you the d naught. Okay. At very low loadings, both will give you the same answers. At high loadings, what happens is that self-diffusivity decreases with respect to the loading. So as the loading increases, self-diffusivity decreases, but most likely corrected diffusivity, which we call d naught, by tracking the center of mass of all the particles together, usually be kind of like will not be affected by the loading. So that means that where you are running, at what pressure, it does not matter. So the last one is the transport diffusivity, so which talks about, based on the fact that we need to calculate the d naught value, which is the corrected diffusivity, times a thermodynamic factor, which will come from the adsorption isotherms. So in adsorption isotherm, what we have is the pressure versus concentration. So that means the amount loading. So using that factor, we can actually calculate the transport diffusivity, which can be compared with the experimental data. Okay. So these are the different diffusivities which we can get from the simulations. So any questions?
So you have mentioned MOF, I think MATLAB Aspen. So what is MOF 5 and G MOF 74? What are the differences?
In terms of pore structure.
Pore structure.
Yeah.
5 and 74?
No, they are numbers, right? What numbers you are referring to is like, so whenever people kind of like come up with a new material, so they will give the numbers. So not all the times numbers have a meaning. So yeah.
And what is ZIP?
Geolytic imidazole framework. Yeah. So that is also a kind of like MOF. Yeah.
And one more question, like what is the pressure, desirable pressure required for operating these MOFs?
You mean to say pressure difference, how much you want to, usually
Yeah, for the sake of adsorption.
adsorption.
What is the pressure I have to maintain?
No, that depends, right? As I said, the amount, like what you are interested in, amount of adsorbed, right? So, so amount adsorbed depends on different MOFs, right? As you see, some MOFs will adsorb, like follows type 1 adsorption, some follows type 2. So when it follows type 1, low pressure will be sufficient. When it follows type 2, we have to go for higher pressures. So we kind of like have to go for it. So there is no like single rule that kind of like says, okay, for all MOFs we have to go like this. So it depends on the type of MOF. It also depends on the type of gas molecules.
And for absorbing CO2, which MOF is better?
I think so far people are using GIF8 and GIF74 is good. That's what, yeah, people have reported simulations and experimentally. But I don't think MOFs are in a good shape to kind of like go for industrialization, because these MOFs are highly crystalline materials. So preparing membranes based on these MOFs is not so easy. So people are still working how to kind of like make it at industrial level. Yeah, so yeah.
So till now for absorption.
COF 20. Till date. Yeah, but like, so that's what we have some flexibility with COF, like because there is no metal inside, but still the the challenge with COFs is that the COFs will have like bigger pores. Oh, CALF20. Okay. Yeah.
Yes.
Okay. Okay, Rajan. Okay, yeah.
So they recently discovered this material called
Okay.
20. That is a metal organic framework. Yes, they
Yeah.
tested experimentally and also the computationally. Yeah, now they are trying to scale up. Yeah,
Scale up,
at
yeah,
the
yeah.
University of Hull.
Did they scale up?
Yeah, they are currently testing on real flue gas.
Okay.
Yes. Yes.
Is there any idea regarding the operating pressure and temperature they are maintaining there?
Well, you can see his papers, very recent papers. I will get you if I have
Yeah.
on my computer. Professor
Arvind
Arvind Rajan.
Rajendra, yeah.
Even MOF 74, my research group has actually shown that in presence of moisture corresponding to it performs well cyclically, but dynamic capacity decreases in presence of moisture by some 8 to 10%, but over 100 cycles or so, the performance is stable.
Stable.
Yeah, MOF 74,
for-
nickel.
Okay.
Yes.
Yeah.
So there is one question from online participant. How would diffusion change if there is a concentration gradient?
There is a concentration gradient.
Yes.
Yeah, yeah. So obviously the flux, right? The flux J right, whatever you write it. So what we kind of like considered when we write the flux is that the flux is directly proportional to the change in concentration gradient, and we kind of like assume that this concentration will not affect the diffusivity. But it will not be the case anyhow, but diffusivity is a function of concentration, and it's kind of like most likely the diffusivity decreases with respect to the concentration. But there are some studies where they kind of like show that diffusivity kind of like increases with respect to the concentration, but in most of the cases it decreases. Yeah. So any questions, Sridhar? Any other questions? Yeah.
Here, you are calculating self-diffusivity.
Yes.
That actually, is it applicable for ionic motions within the matrix?
Ionic motion within the?
Matrix, the solvent matrix actually.
Okay.
So, can we use it to
With the ionic, with ions?
Yeah.
Yes, yes. You may be referring to lithium ion, right? So yes, it can be. We can use it for lithium ions. Yeah. Yeah.
This isosteric heats of absorption.
Isosteric heat absorption.
This mainly depends upon the amount of absorbed material. I have seen on the graph in which it was shown that the MOF is absorbing more things. For the PST, that's isosteric heat also very less. What is the reason for that?
Isosteric heat of absorption.
Other geolite and other things.
Yeah,
Less isosteric, everybody is absorbing more.
it can absorb more, but it also depends on the interaction between the gas and the solid. So how strong the interactions. So if the interaction is very high, like what you see in geolites like silicon and oxygen together, so there the interactions are pretty high compared to the MOFs. So yeah, here less interactions. Yeah, yeah.
So one material is there, so activated carbon.
Activated carbon, that is very less, like the carbon only related stuff, right? So
This absorption mainly depends upon the area of the surface area.
Ha. Oh, no, we are not talking about the surface area and all. We are just talking about like given the material, how much heat it kind of like releases in terms of isosteric heat absorption. Yeah, and some.
The point is what I'm thinking when we are talking about temperature or heat and trying to correlate with absorption. If temperature is same, for example, say the room temperature. Gas is near the room temperature, and you wanted to separate mixture of gases from CO2 from other gases and other things. Keep its temperature as same temperature. Material or surface material also same temperature. How that the temperature is increased with respect to absorption?
No, when the gas molecule adsorb onto the surface, right, it releases the heat.
Considering the same temperature of the gas, medium and the surface material.
Right.
both are in the same temperature, when it's getting adsorbed,
Uh-huh.
how the temperature will increase, or that, or
No, no. Okay, so because of the attraction energy, right? So when the gas molecules come and sit onto the surface, right? So the heat will be released because of the interaction between the gas molecules with the surface. So that's the kind of like the what you call is the driving force for the gas molecules to come and sit onto the surface. Why a gas molecule will come and sit onto the surface? Because it is kind of like attracted towards the surface. When it comes and sits on the surface, it kind of like releases the heat. So that heat has to dissipate. So anything?
very accurately that the heat generation.
No, that can be.
Availability something to, any instrumentation something.
Yeah, that can be measured like different techniques like calorimeters we have, and or else we can measure from the adsorption isotherms. That's the two ways we have. Anything, Sridhar? Sridhar, anything you want to add?
So Clashes-Clapeyron equation also we can use. Clashes-Clapeyron equation we generally use. If we have isotherms, we'll model it, then we will substitute in the parameters what we obtained, and to get the delta H. That is the one way. And as he said, there are calorimetric
Methods.
equipments also there.
Yeah. So yeah, we have two ways. One, either use the calorimetric methods or use the adsorption isotherms. That's what Clapeyron equation. Yeah.
Shall we take a short 15
Break?
minutes break?
Yeah, okay, fine. I'm like, you have any question? Maybe 5 minutes or?
So in between we can discuss.
It's okay, all good? Okay.
Okay, everyone. We'll come back in 15 minutes.
7. Then 4, 5, 6. Okay. Yeah, right.
Yeah, continuation. No problem. Okay, start this. Okay, start this. Welcome back, everyone. We'll start the lecture 6. That is on kinetics and also the breakthrough of the gases. Dr. Ravi, you can continue, please.
Okay. So talk about breakthrough. So why breakthrough is important and what is breakthrough? So these are the two things which we kind of like discuss, and then how we will perform the breakthrough experiments and how we analyze the results, right? And then we kind of like try to see what models we can fit it. Okay. So dynamic breakthrough experiments is a powerful tool to assess the effective sorption capacity of a porous material. So what we do is that we kind of like have a packed bed kind of setup, and we allow the gas molecules to flow through it, and then we kind of like try to monitor the concentration of the gases at the outlet, right? So what we kind of like do is that with respect to the time, so we have a packed bed, something like this, and here we fill with the material we wanted. So we kind of like we design the geolite, MOF or whatever, right? So we fill with that, and then we try to kind of like allow the gas molecules to enter into the system. And then what we will do is that here we will monitor what is the concentration of the gas with respect to the time, right? So what happens when the gas enters into the system? Here whatever material we have adsorbed, we try to adsorb all the gas molecules. So with respect to the time, what we see is that we don't see any concentration of the gases at the outlet, right? So it's kind of like when you kind of like plot it, time, and see the concentration here, what we do see is nothing. So we'll say kind of like, okay, 0 concentration all the time, right? So after some time what happens is that, so as the gas flows through it, right? So we do see a slight increase in the concentration after some time. So that's when we call the gas breaks through, right? So when we see the first, like whenever we kind of like observe the gas concentration at the outlet, that's what we kind of like say that the gas break through the packed bed, and that time is called breakthrough time, TB. So which we kind of like go through it, right? So this is how a setup looks like. We have a mixture of gases, we are mixing whatever we wanted, and then we kind of like have a packed bed where you put all the materials, and here we have like kind of like woven. Say for example, if there is any water or anything, we kind of like try to evaporate and everything like that. So the gas enters from the top. So here we try to kind of like measure the temperature and pressure difference. So here when the gas molecules enters, we measure the pressure. When the gas molecule leaves, we measure the pressure. And then we kind of like goes through a sample collector. So that's kind of like typically maybe this kind of like thing which kind of like used to measure the composition of the gases. Sometimes it may be GC, sometimes it may be mass spectrometer, sometimes it may be FTIR. So depends. Okay. So this is how it looks. So this is kind of like how a machine looks like. That's what I just want to show. So these are the walls where you kind of like see the gas which kind of like allow the gas, these walls will allow the gases enters into the system. So these gases like flow through this one and enters from here, okay? And here we kind of like have all the material, and then it kind of like leaves from here, and we measure the concentration at the outlet. Okay. Right. So how we kind of like perform this experiment? We kind of like do it in 3 stages. First, we have to prepare the sample. Second, we have to activate the sample. And third one is we do the breakthrough analysis, right? how we do the sample? We kind of like first prepare the material. So either by pelletization and sieving and disperse sample in a glass beads. That's how we kind of like prepare the packed bed stuff. And then we need to do some additional considerations when we kind of like preparing the sample. So what are those? So it's something like this. So when you are preparing the sample, so either you can prepare like a large bead something like this or a small bead something like this. When you go, therefore it offers a lot of pressure drop, right? When we go for a large particle something like this, so then what happens is that this gas molecules which enters into the system has to go through this bigger particles, offers a lot of kinetic resistance, that means diffusion resistance, right? So we kind of like have to see what kind of things we wanted, right? So when you kind of like prepare the sample, you also need to see what kind of like, when it kind of like enters into the system, what is the diffusion paths. It's a diffusion path is a straight one, not is kind of like a zigzag path and so on and so forth. So we also need to see all these things when we prepare the sample. So which is a very important one, right? The second one is the activation. So activation means that when you prepare the sample, you don't know what kind of like gases are present inside. So this activation is to remove all the gases which present inside. So that's what we kind of like either do one of this. In the vacuum we will heat it, or we kind of like send the gas through it and heat it. And it's kind of like dependent on sample to sample. We don't follow the same technique all the time. So it depends on the sample, on the material, on the sizes and so on and so forth. Once the activation is done, we do the breakthrough analysis. That means we let the gases enters into the system, right? And then we kind of like try to monitor the gas concentration at the outlet. Okay, this is the anyhow. So then we kind of like try to see with respect to the time, the concentration, right? So as we said, initially when we start the process, so all the gases will absorb into the system, therefore the initial concentration will be close to 0 at all the time. So this part is called where the complete adsorption is happening. So this is like here where we have unsaturated bed. So this is complete adsorption part. In the second stage what happens is that once the gas breakthroughs, right, at the breakthrough time, it goes through the breakthrough, and after that we reach a stage called saturation. So where whatever gas we send, it will come out. So these are the three stages. One is complete adsorption. So adsorbent completely absorb all the gas molecules, therefore we don't see anything at the end. Second one is breakthrough. So adsorbate gas is first detected at the outlet, and gas continues to absorb in the adsorbent. However, it's no longer able to absorb the entire gas. It may be partially absorbing something and partially releasing something. So that is a breakthrough region. And the saturation region, whatever gas you send in is coming out because it's already saturated. So whatever gas goes in comes out. Right. So how we do this one is that we kind of like calculate the amount it absorbed with respect to the time. So that is Ci is the initial, Ci is the concentration at any time t, which is final time. C naught is the initial concentration. Vi is the flow rate, and dt is the time. Okay. So what you see here is that in general we don't kind of like use the dead time and the final time. We kind of like go from 0 to t, but whenever we kind of like doing it in an experiment, we use the dead time. So the dead time is nothing but, say for example, you kind of like sending the gases from here, and then it has to flow through all these pipes and then come and then go to the final stage. So it requires some time. It is nothing to do with the adsorption. It has to flow through all the pipes and the regions inside. So it takes some time. So we kind of like have to avoid that one. So for that one, what we usually do is that we kind of like perform. So this dead time is nothing to do with the gas or anything. It is only to do with the flow rate. So what we usually do, say for example, we are running this experiment at a given flow rate. That means Vi, we know the Vi. What we do is that we kind of like start an experiment something like this. So we have T versus Ci minus C naught. right. First initially we kind of like send a tracer gas which does not adsorb into the system. So then what happens? So the tracer gas kind of like goes like this. It's maybe a sharp curve you will see here because there is no adsorption at all. So this first we perform on a tracer gas, right, this. So then we kind of like replace the tracer gas with the gas we wanted and then see. Something like that, right. So the area under the curve which is in between these two things will give you the amount adsorbed. Okay, that's how we calculate the amount adsorbed. Okay. Yeah. So this is tracer gas which does not adsorb into the system mostly. Helium, hydrogen still adsorb little bit, but most likely helium is the best one. It will not at all adsorb.
So when we start flowing our tracer gas, its concentration at the outlet won't change. Because no other gas to be detected, right?
No other gas will be detected, it will detect the helium. So we will start with only helium first, right. So we will not perform these two things at the same time. Yeah, first we will do with the helium.
When we do the tracer gas,
Right.
how are we measuring that C by C0 for the tracer gas? Because there is no other gas, it will always be one.
Right. So that's why when we kind of like go to the breakthrough time, that's the equivalent to the dead time, it sharply increases from 0 to 1. That's what you see here. Unlike here, which is actually going through a phase like this, when we kind of like run with a tracer gas, what happens is that, so this time is not the nothing to do with the saturation. This time is the dead time. That means the time required for a gas to flow from inlet to the outlet. Once it reaches the outlet, what happens is that the concentration sharply increases from 0 to 1 at the outlet. Yeah.
When we start the tracer gas actually,
Yes.
what is the inlet gas actually?
Inlet
Only pure tracer gas.
pure tracer gas, right.
Then how can we measure from 0 to 1? Because the detector will give only 1. Because the concentration, there is no other gas,
No other gas, right.
right? So it will always be 1.
Yeah, but to reach 1, how much time it will take? That's what we are interested in.
Okay.
Yeah. Okay. So this is how we kind of like a breakthrough curve looks like. So this is the region where you see complete adsorption, right? And then a breakthrough and then saturation. So the time here you see TB is the breakthrough time. So you may say like, why not here? Why here? Is that is where exactly we have to do is not in our hands. It's actually a limitation from the experimental side. So how much gas it can detect? So we may not able to detect when the like maybe in a very low concentrations. So maybe at least it should have a little bit. So maybe like around 5% which we consider. So that time only we like our machine will able to predict it properly. So that's why like this is the TB, which is called breakthrough time. And once we reaches almost 100% saturation, even here also we kind of like say go with 95%. So that's called dead time, right? So the difference between TD minus TB is called the mass transfer zone. So which you kind of like have to have the information to understand the analysis of breakthrough curves. Okay. So any questions on this one? This actually this breakthrough curves will tell you like how much gas it can absorb onto the system, right? So this is the information which we will get, which will be useful in designing the adsorption systems. So whatever adsorption isotherms or kinetics we have, that will be helpful in screening the materials, but this will be helpful in kind of like understanding at a given flow rate how much it can absorb and at what time it needs to be regenerated.
So 100% of the gas is being absorbed. No gas is slipping through the pores without being absorbed. Is that so perfect?
So it may not happen. I'm like, so that I understand, but it depends on the packing and all. So how good the packing it is and all. So that's all kind of like goes into the sample preparation. So as you said, like if you go for a bigger particles, obviously the diffusion can happen between the particles. So then it may not be like perfect mass transfer situation, but we assume like in an ideal case, it will happen something like this. Yes.
You actually pass the first trace again. So like there's a time in between where actually it has to leak from 0 to 1. So that is actually the system's dead time.
Yes.
Then this TD there actually after saturation, is it the same? It won't be the same, right?
It won't be the same. Yeah, yeah.
So what does it mean by TD at that point?
TD is the dead time is only not like TD is only to do with the gas of our interest, right? So whenever we kind of like see here, especially when we go for the tracer gas, right? So the breakthrough time and the dead time is exactly same because it will not absorb anything. It is only just time to pass through. Yeah. Yeah. Right? Yeah. And yeah, that's all. Okay. So then we kind of like go through a batch adsorption process. So like usually batch adsorption process is often used when we have like small amounts to be absorbed, right? What we kind of like do is that, like especially for liquid solutions and so on and so forth, kind of like have a solution, then put a adsorbent into here, right? So then try to analyze the mass transfer here. Okay, so what we will do is that like we kind of like put a solution and an adsorbent here and try to measure the concentration in the solution with respect to the time. So the remaining solution is adsorbed into the solid. Okay. So yeah, so this is a simple mass balance equation, which you see that the initial feed concentration is CF. That means whatever you have here is initially CF, right? And the final equilibrium concentration is C. That means after everything happened, the adsorption process is happened after time t. So the final concentration is C. So the difference will go into the solid. So that's what like you can see that the amount adsorbed will be calculated using a simple material balance like that. Okay. Anything else? Nothing interesting? Yes. MFCS, yeah. Okay. So then we kind of like look into the adsorption kinetics when a batch process something like this happens. So right. So as we kind of like discussed, one of the most important parameter is the rate of adsorption, rate at which the adsorption occurs. So therefore adsorption kinetics helps in determining not only the interaction between adsorbate and adsorbent, and also we kind of like get the optimum adsorption capacity and then potential rate limiting steps and so on and so forth. So governed by the surface complexity of the adsorbent, solute concentration and flow, the adsorption kinetics may be very different in all the situations. So some kinetics may foretells the adsorbate-adsorbent interactions. So based on the kinetics, we can say that okay, it's kind of like a physical adsorption is happening, chemical adsorption is happening, and so on and so forth. So we kind of like also say the interaction between them. All right. I think we can skip this one, but so the only point here is that we kind of like talk about the adsorption kinetics now, like the curve. What we try to monitor is the concentration with respect to the time and try to fit the data. So whatever we have here is the concentration, sorry, the time here the concentration here, then try to monitor how it goes, or how it goes. It depends what you measure. So where you measure, that means that whether you are measuring in the adsorbate or in the adsorbent or in the solution. So, and try to fit the data there. Right. So usually what we do is that we kind of like in batch process, what we do is that we measure the concentration with respect to the time and try to fit with one of these models and try to understand what is happening. So these are all the models. So it's kind of like only purely based on assumptions that we kind of like see that. I just want to go one by one quickly. So the first one is the pseudo first order model. It describes the adsorption kinetics by assuming the rate of adsorption is directly proportional to the difference between the equilibrium and current adsorption capacity. It does not consider any mechanisms like surface interactions or diffusion process or anything. It only says that as long as there is a concentration gradient, the gas molecules or any molecules will adsorb into the system. So this one pseudo first order typically used for the liquid phase adsorption systems, because whenever we deal with the gases, we should kind of like have to consider the diffusion. So usually when we kind of like deal with the liquid phase systems, we go with the pseudo first order. So as I said, here the kinetics, rate of adsorption is directly proportional to the difference between equilibrium and current adsorption capacity. So the equation we will write something like this. Qt, which is the adsorption at time t, is actually proportional to QE minus QT. So QE is the equilibrium one, that means the final it can achieve, and QT is the current one. So the difference in the concentration gradient is the driving force, and K1 is the rate constant. If you just integrate it in the limits of from 0 to t, so when time t is equivalent to 0, Qt is equivalent to 0. Right? That means initially there is no solute present in the solid, and at time t, at any time t, Qt will be there. So you just model it, you just get an equation like that. Right. So that's the one first. So when we got the kinetic data, right? So when we have the kinetic data, we can use this equation and try to fit it. If we are able to fit with this linear equation, so that we say that it follows pseudo first order model. So that means that mostly concentration gradient is the one which is kind of like the cause for the adsorption, or like mostly rate limiting thing. Okay. So the second one is pseudo second order. Even this also can be kind of like mostly used for the liquid, to model the liquid systems. So it describes the adsorption kinetics by assuming the rate of adsorption is directly proportional to available sites in the adsorbent. So the first one talks about the difference in the concentration, but this one talks about the available sites in the adsorbent. Okay. So here the governing equation is dq over dt is equivalent to K2, which is another rate constant, is and times QE minus QT whole square. Okay. So this pseudo second order model may be affected by pH, the amount of dosage, particle size, temperature, and so on and so forth. So this model assesses the impact of observable rate parameters. So only one important thing here is that, so again like same thing, you take the same boundary conditions. At time t is equivalent to 0, Qt is equivalent to 0, and then there are several forms available. This is one of the form which I have mentioned here. So it looks like what you see in Langmuir type of adsorption isotherm. So you kind of like fit into a graph t times Qt versus t, you will get a linear equation. If that is the case, then it follows a pseudo second order model. So what people kind of like believe is that whenever they observe kinetics with the pseudo second order model, they assume that it is something to do with the chemical adsorption, because whenever there is a chemical adsorption, they observe this is the case. So, but please note that whenever you observe pseudo second order model, it does not mean that chemical adsorption is happening. If chemical adsorption is happening, you can able to fit the data with pseudo second order model. But whenever you are able to fit with pseudo second order model, it does not mean that chemical adsorption is happening. So the other way around is not correct. Okay. So what you have to do to verify it, you can go, yeah, so this is the one. So yeah, like say. So then what we kind of like have to do is we kind of like try to fit with yellowish model, right? So this kind of like developed to especially to take care of chemi-absorption. So it kind of like predicts the mass and surface diffusion, activation and deactivation energy of a system. So initially it kind of like proposed for a gaseous system, but it has been applied to many liquid systems as well. So this model assumes that rate of adsorption exponentially decreases with amount of adsorbed solute. So it looks something like this. dq over dt is equivalent to alpha times exponential minus beta qt. Alpha and beta are rate constants. So alpha is called initial adsorption rate. That is because when qt is equivalent to 0, that exponential becomes 1. So that dqt will be alpha, that is initial adsorption rate, and beta is the desorption rate. So it kind of like considers both adsorption rate and desorption rate and kind of like takes care of everything. So integrating in the limit of, again at time t is equivalent to 0, qt is equivalent to 0. So it can be linearized as this form. So you can kind of like plot qt versus logarithm of t. You will get all the parameters you wanted. So from the slope you will get 1 over beta. From the intercept you will get 1 over beta times logarithm of alpha beta. Okay. So this is kind of like applicable to both gaseous and liquid systems. So one we are very much interested in is inter-particle diffusion model, right? So this is the model usually used to describe the diffusion controlled adsorption process. So whenever we kind of like deal with gas adsorption in a solid material, it is controlled by diffusion. So this intra-particle diffusion model is most likely be used to fit gas adsorption data in a gaseous system. Okay. So this kind of like considers the adsorption of a solute in the solution has to go through all these diffusion things. One is the film diffusion, 2 is the surface diffusion, 3 is the pore diffusion, right? As we discussed, what happens is that whenever you have a solid particle like this, right, and then you have a pore like this, right. So whenever we kind of like try to perform an adsorption, then what happens is that some gas molecules will adsorb onto the surface. So that's maybe near the surface. So it forms a stagnant film like thing here, somewhere here, because of the interaction between the solid and the gas. Okay. So whatever gas molecules that enters, right, it may be coming from here, it may be coming from here, it does not matter. It has to flow through this film kind of thing. So this film is happening because of the solid gas interactions. So it has to kind of like flow through the film of liquid or gas to enter into the system. So this is called film diffusion. So this model will take care of the film diffusion. The second one is the surface diffusion, which we kind of said, not all the gas molecules will enter directly like this. It may have to kind of like go through this. So that surface diffusion it has to take care. And the last one is the pore diffusion, that's like what is happening inside. So this model will take care of all three. One is film diffusion, second is the surface diffusion, third is the pore diffusion. Okay. So this model particularly useful analyzing mechanisms of adsorption in porous materials, which is of our interest, like activated carbons, zeolites, MOFs or whatever. So it kind of like follows something like this. So Qt is the adsorption capacity at any given time is equivalent to Kp, which is the rate constant, times square root of T, that is the time and see. So this is a very easy model. What you kind of like has to do is you just need to fit square root of time with qt, that's it. So it should be a straight line with a slope of kp, then the constant. Intercept will give you a constancy. Everything else will be taken care of. Okay. Yeah. So any questions and breakthrough on the models? Yes.
This KP, what you were saying, does it have any correlation with the diffusion?
With diffusion coefficient? Yes, it will be, because it kind of like takes care of all the diffusions. But what diffusion coefficient we need to see, whether we are talking about the yeah, most likely the D, which is like, say, although we kind of like say in terms of resistance I will talk. So we said like there will be three types of resistances. One is like going through the film kind of thing, and then the surface, and then inside. So the resistance which we get, like this intra resistance, is pretty high compared to these two things. So most likely the diffusion inside is the limiting step. So this D is kind of like related to Kp, because these two things are most of the times negligible. So this D is kind of like, yeah, related to Kp. Right. Any questions? Any online questions? Sridhar? Yeah.
So we have some time left. If you want, we could go through the topic again. Is everything clear?
Okay, that's good. They have, okay, so all good. So thank you so much. If you got any questions, yeah, please feel free to write to me. You have my email ID somewhere there. So then, yeah, and I will be mostly available, yeah, till end of today, and then yeah. So if you got any questions after that, then I'll see through email. Okay, that's all. Thank you so much. Thanks everyone.
So this is the last lecture by Dr. Ravi. In case if you would like to discuss, so you can drop a mail to him. Okay, email ID we will provide, and he will be available till evening. Okay, everyone. Thank you. So our next lecture will be from Dr. Debanshu. We will start in a few minutes.
he seems to like that work actually. Already? Okay, good morning everybody. So the first thing that I would like to say that these equations, I just put it here because you are very familiar with this equation, right? This is the fundamental equation that we have all come across from BSL, from your transport class, and this is a partial differential equation, right? And so what we do is we take an equation like this, and then at the top of it, we add the algebraic constraint, and that gives you the PDAE. So like when we look into the species conservation equations with the solid sorbents, that whatever temperature picks up, who takes away the heat? So only the flowing gas will take away some of the heat, but as we know that the specific heat of the gas is very small, so they cannot really take much heat. So it's only through the flow rate you will get some heat out. So quite often that's why you have an embedded heater or a cooler. So you put a heat exchanger locally through a cooling water will be wrapping around, and without that you may not have really achieved much adsorption at all. If your heat of adsorption is high, an embedded cooler may be needed, right? So those type of, when you consider those, this is the term that will capture it. So I just put it like a catch-all term, right? This can cover many things. With these equations, any question here? This is very generic, and but we will be taking these equations. Basically, this is where from the adsorption models are obtained. Everything is in Bird-Stuart-Lightfoot. Everything. It's only some modifications you do, but everything is, you can directly get it from Bird-Stuart-Lightfoot. All the fundamentals are there. Okay. Now we go. Okay. Right. Right. Correct.
Is it necessary to include convection here? Only can you go with only conduction?
Yeah, this is just the entire equation, but you have to really see what else is going on. So some cases you will see, like when we will go into the specific equation, I know Dr. Pala is also going to go about those equations. I will also cover some of those equations. You will see that we do not use all the terms everywhere. Like for example, when we are considering within the pores, right, then we'll be mainly talking about these terms there. When we are considering the bulk flow, we'll be mainly considering these terms here. So we'll be keep doing it. Radiative heat transfer, because the temperature remains very low, it's generally very negligible. But if you are operating it at a high temperature because of some reason, then yes, you can consider that. Yeah. Okay. Very good. So I will go back to the same problem here, that what we had is that when we try to do a dynamic model for a PFR, and you see that here I did not consider this. So this is the same term, same equation that I took, but what I did was I neglected all these components over and here, and just I retained only this term and this particularly this term. Those are the only two terms that which we kept. This is for simplicity. You can consider more terms there, but this is a simple model that which you have read in Levenspiel's books or Fogler's book, and this is a simple equation that which we considered that. Why I'm actually showing it here is that because in the afternoon, that demo that I will do, I will show you some of these things. Other things will take you a lot of time. So it's a simple version that is amenable to in this class actually, and see how we can actually solve it. So, and then other equations that which we have for a PFR model. So the point here is, without this, it is a steady state model, and then when we are doing it, this will be a dynamic model, right? And what in this class, what we really need to be very much used to is the concept of dynamics and change in both space and time. Generally what we do is that either we consider time derivative, we neglect spatial derivative, as I said yesterday those are lumped model, or we ignore the time derivative, we only consider the space, and those are steady state model. But these systems, the adsorption systems, has got both change with time and space. So we cannot ignore any of these. So this is the type of model that we need to get used to it and understand. So you'll see I'll always be keeping talking about the dynamics and all of those stuff. So please stop me if there is any difficulty in understanding. But before I go forward, if I say, okay, this is a steady state model versus this is a dynamic model. So let's have a quick discussion. If I'm considering a PFR, right, we have all started, like starting from our undergraduate classes, we do plug flow reactor, and we do not solve them dynamically in the undergraduate, like it's mainly solved steady state. So when we solve for steady state and when we solve for dynamic model, is it arbitrary that I should solve for dynamics at some point of time and steady state at some point of time? When should I consider dynamics of a plug flow reactor? Anybody? Startup, right, excellent, or just startup condition, shutdown condition, or when actually there are changes in the boundary taking place, right? Practically, if you go to an industry, like in our classroom type of an example, we consider the composition is constant and blah, blah, but in reality, they are not. There is never like a constant composition feed is coming in. Think about a petrochemical refinery. Think about coal. Think about a natural gas. This is coming from under the ground. The composition is actually always keeps changing. So it's never that steady state. We just approximate it as a steady state. We say, yeah, it's reasonably close to steady state. But adsorption is something will never have a steady state. So this assumption is not possible for an adsorption, and as we keep discussing this, you will see that why it is not. There will be more discussion tomorrow. Now question is that if I give you a problem like this, how do you solve it, right? Even like a simple problem like this, there are two derivatives. One is with respect to space, one is respect to time. So how do I solve this problem? So in the numerical world, the most common approach is called the method of lines. So in method of lines, what we do is we discretize in all but one direction. So we never discretize the time domain, but we discretize the spatial domain. So remember yesterday's class, I was talking about finite difference schemes, right? I say backward and the forward and the central difference. So what you really do, you take this one and you apply one of the forward or backward or the central difference schemes. Once it is done, this becomes algebraic equation. But what happens is we are not losing the concept of the space. So essentially what we are doing is if I have a plug flow reactor like this, when I am discretizing it, I am considering each of these locations. So I need to solve this problem at each of the locations. So I need to solve dci dt here, dci dt here, dci dt here, dci dt here. All of these locations I need to solve this same problem because I discretize it. The discretized is the space, but this time derivative remains. So I need to solve these equations at each of these places. So if I am discretized more, simply speaking, I am actually increasing the number of the time derivative that we are considering, that I need to solve. So if I do discretize it into 1000 pieces, so I need to solve 1000 of these equations, and that makes it complicated. So more discretizations makes it more accurate and more computationally expensive. But this is the technique by which we go. This is known as the method of lines. So what it does is that we take the PDAE, so it will convert these to a DAE, differential algebraic equation, which we discussed yesterday how to do it. However, what I discussed yesterday was that we talked about the finite difference schemes, but we applied that to spatial derivative. Now we have a DAE, but instead of the spatial derivative, we have the time derivative. So this is different. So remember yesterday when I was discussing about DAE, I was just simply talking about this guy over here, right? This was spatial derivative, and we applied the forward or the backward or the central difference here. But now we already discretized, we are left with this guy. This is time. This is different. So time cannot be treated the same as the space. They are equivalent, but I said time cannot be treated more similar to space. In terms of, you can apply similar scheme and the thought is the same, but it cannot be treated the same way. Anybody has a guess why we cannot treat the time as the same as the space?
So the time-dependent problem has only one boundary condition, the initial condition.
Right.
In space you can have two boundaries.
Exactly, that is one of the thing, and then the spaces can be coupled, but time at future time cannot impact the current time. Like I cannot say what will happen 2 hours from now is going to affect at t equal to 0. No, it cannot. But in the space it can be completely coupled, and then what is happening downstream can affect upstream, because you can clog something and the flow will go down, or you might have a pressure drop downstream and you cannot do this. So this is one of the very key differences between space and the time. So we can take the liberty, we say, yeah, for the time I'm actually marching forward, but the time has a problem. In the space, we are bounded. We are basically saying, this is my reactor size, or this is my distillation column size. But space, with time now, I can solve for 1 day, 2 days, 10 days, 10 years, 30 years, 1 million years, like if I'm doing for CO2 sequestration problem, people are simulating for million years, right? That basically saying, well, I'm storing CO2 somewhere, maybe can it happen that one day that CO2 might come out and kill everybody around that neighborhood, right? So those are a million years simulation that people are trying to solve. So it depends what you are trying to solve here. So that's one of the differences. So the thought is the same, but there are some fundamental differences. I will be discussing here, and it's also implemented in, I think MATLAB does not have an implementation of a lot of these approaches, only some variants of it. ACM has, the Aspen custom modeler has the implementations of this. In Python, there are actually some implementations of these ones. So this is a very powerful technique, and I'm sure as part of your numerical methods class, some of you have taken and understood some of this. So I'll recap some, but I will talk about more practicality of applying these approaches also. So what we are trying to do here is, once I discretize, this is the problem that I'm trying to solve, right? We have got many of these equations. So this is the general linear multi-step method. So massive amount of variations of these yield all the techniques that you have learned in your class. As you are changing these things, like how many terms you keep and how you actually compute this, you will get all kind of equations. You can get explicit Euler, I will show you, implicit Euler, you can see all the techniques from Adam-Basford type of techniques, and all of these other approaches that you will find with first order, second order, third order, fourth order, all will come from these general equations. Okay. So here, this is how you generally solve these problems, and then based on these you cannot retain, like question is how many k's you keep, how many m you keep, that is where the order and the error of the terms keeps changing. Okay. So here alpha naught equal to 1, alpha 0 equal to 1, that basically means that I am predicting for yn plus 1 starting considering yn and other terms, right. Now note that if I consider that beta naught equal to not 0, that basically means that I am keeping the 0 term over here. So we will have f of x n plus 1 y n plus 1, that basically meaning that I am considering y n plus 1 depends on f of x n plus 1 and y n plus 1, right. So ensure that that is getting clear as it is written. So if you substitute, if this is not 0, that basically meaning is, and I already put y alpha 0 equal to 1. So if I am doing it, so this is 1, so this will be y n plus 1. So I am saying y n plus 1 is equal to whatever, and then something, and then I will have f of x n plus 1 y n plus 1. Sorry, it got probably so close. Let me write it here. Okay, so y n plus 1 is equal to bunch of terms plus bunch of terms, and f of x n plus 1 y n plus 1. You see everybody? So that basically saying is that this depends on this. So the when it depends on the current step itself, it becomes an implicit method. So there are all methods that which we are talking about becomes an implicit method. If it is not, we call it an explicit method. Okay, that's why we do the implicit Euler, explicit Euler, like we have always done that, right. Can anybody recall that what are the mainly the issues that I am sure as part of your graduate class we all discussed, that what are the issues with the explicit approach, because implicit makes it very difficult, right, because when I am trying to solve this, but I am saying this depends on this one, so I have to solve this together. In fact, if I could actually make our life a little easy, and I simply say x n and y n, this becomes an, in this case it will become an explicit, right, and that makes it easy, and the first order explicit method is an Euler's method, explicit Euler. So what was the issue with this explicit method? Sorry? Error keeps increasing, and so for decreasing that, the time step has to be very, very small, very small. So you have to take many steps there, right. So as we all recall that. So now this approach is called multi-step if this is greater than equal to 2. Like if you substitute it, so say if I am considering it j equal to 2, so then I will get n minus 1. So this will becomes function of terms like we will have f of x n minus 1 y minus 1 and similar terms, right. So as we keep increasing, when we have these previous terms being considered there, then we call it a multi-step approach. So I am saying I want to find out the value at y n plus 1. It not only depends on n or n plus 1, but it also depends on n minus 1, or maybe even going forward I can consider of x n minus 2, y minus 2, and so on and so forth. When I consider these are called the multi-step approaches. Okay. If the order of the method is p, and we will be talking about that, like this is the kth order that which we consider here, then the local truncation error. So this is always will be defining this local truncation error. This should be of order 8p plus 1. That basically means is if I am actually considering a first order method, so this will be order 2 and so on and so forth, and I will show you in a moment. Then these, so what are unknowns here? These alpha I and beta j. This is the coefficient equation that you need to solve, and q is equal to 0 to k plus m, and when as you keep substituting it, you will get actually bunch of equations together. Is it not working?
It is worked, but there are some disturbances.
Right. Okay. Yep. Thank you. So this is the, so basically what you do is that you take this equation, set alpha not equal to 1 and solve these equations, and then you are good to go with many different type of integrator. You can discover many different type of integrators. In fact, actually when this equation showed up, people realized that actually lot of the standard integration approaches came from this general equation. So you can apply these equations to lot of integration techniques, right? So if I take these two equations, and then this is a very busy slide, but I will keep going back and forth. If I would say k equal to a1 and m equal to 0, so that means this equation k equal to 1 and m equal to 0, that gives me that implicit Euler method. And you can substitute all kind of numbers there before, and you will see all kind of Adams-Moulton, Adams-Beresford, all equations, everything will actually show up there. One of the powerful method I would like to note here is that, which I will suggest you use in Aspen Custom Modeler. I think this is not yet implemented in the MATLAB ODE suite, but it's there in Aspen, is called the Geertz method. This is kth order backward differentiation formula, Geertz method. So what we really do there is beta not equal to not 0, all other betas are 0. So that means here I'm only keeping m equal to 0. So we just keep m equal to 0, and then and then I can actually, if I do that, this is the equation that I get. So if you notice here, this is the overall equation that I get if I set m equal to 0, because there will just be only one term, but this will all remain there. So from here, as I keep changing the value of k, I will get different order. So these are the errors that I will get, and how we are getting these coefficients here. These coefficients are obtained by solving these equations. I'm just not doing it, showing it here. You can find it in numerical methods book there, or you can even solve it yourself, like substituting these equations and solving for those coefficients. But this gives you a varieties of method. So when you go to Aspen Custom Modeler, it will give you an option, say Geertz method, and it will say maximum order, and you will say yes, 6 or 5 or whatever. It's up to you. Then what it does is that if it will start with that maximum order that gives you the highest accuracy. If it cannot solve it, it will keep cutting. So it will say, oh, I start with the 5th order and I could not converge, then it will go to the 4th order. It could not converge, it go to the 3rd order. It could not converge, it go to the 2nd order. It keep going. This gives you a lot of flexibility in terms of the solving the system of equation. But when you click those, and I will show you today where it is, when you click those, you know this is actually what is happening. So higher order means the lesser error, but it can be computationally more difficult because you are seeing that what terms it is actually keeping, and then it becomes actually more difficult for it to converge. And it is okay to actually go for an higher error. So remember, like generally as a researchers, we always want the highest accuracy. But one thing you have to always keep in mind is the stiffness of systems. So when a variable changes like this, it goes like this. This is extremely steep. It's almost like a vertical line. Most solvers have trouble in getting into that. But if you really want to get the results, one, if it is actually instead taking a step something like this actually ease out it quite a bit. Just a little shifting, instead of saying it's like a vertical line, you just actually have a little bit of an error somewhere around this zone here, and you will be fine. So remember that if you ever seen an industrial simulator, I'm not sure anybody has seen an industrial simulator, like many refineries I know they have it, they train their operator before they actually operate a plant, they take you to a simulator and train you there. Those simulators actually do these things routinely. They live with an error. Basically they say, yes, it's fine, I live with an error, but I'll catch up in the future. So this is living with a little bit of an error and inaccuracy, and then you go with it. You can actually say, no, I don't want to live with an inaccuracy, then it can have a convergence failure. But this will, at least you will get some convergence, and you can then compare how the results look like. But can anybody anticipate what is one of the issues with any of these approaches? What gets involved? Like, for example, you might argue that yes, this is the same function that I'm actually solving. So what is the issue when I'm actually keep increasing the order? Yeah, so you are increasing these guys, right? So you have all of these terms to keep holding on to all the variables here if you click one of these, but it is also because of it becomes actually, it constrains the overall system of equations. So with this additional term, so it makes it, it can make it more difficult for you to converge all of those. Anybody has any question so far?
Sir, higher order will also increase problems with the boundaries.
Yes, it will. So, and especially when you, with respect, there are two things which we'll be discussing in a moment there. One is with respect to t equal to 0, and one is with respect to the spatial boundary. The question is there a stiffness around the boundaries? So how you actually handle the stiffness at the boundary? It could be a time boundary, like at the initial value problem, or it could be a spatial boundary. And Aspen gives you all the flexibility to saying, yes, like as I was showing you here, you might actually relax it. You can actually, in the spatial boundary also, you can relax it. You can actually have to put more discretization in the spatial boundary. So there are a lot of options that is there. So quite often around the space or the time, there may be issues in terms of convergence. Yes, absolutely, you're right. Any other comment here? Okay, now comes our favorite. We all like this fourth order Runge-Kutta method. This is the standard approach that which we have all done this, and then this could be also different orders are possible. Fourth order is very common, and you can adjust all of these things, and this is, we have always done this, right, as part of our undergraduate and graduate classes. One thing that I wanted to say, this is generally many times we do not teach in our classes, is that something called an adaptive step size. This is important for the solving steep problems. One of the confusion that comes there is, what should be your step size? Should it be 1 minute, 2 minutes, 1 second, 0.1 second? How do I know as an user what should be my step size? Because the solution that you are trying to get depends on what is your step size. So, let us see that we understand what is the issue with respect to the step size. Why does it matter to have the step size? So, think of your y with respect to t changing like this. Say if I have a large step size like this, say this is my step size, how much this variable is changing? This is jumping from here to here. This is a very tough problem for any of the solver to solve, linear equation solver and a linear equation solver that will finally solve everything, right? But is this value a good initial guess for this one? No, it's really far away from this. So, during this time I may be like to solve here. So, I have to cut step like this, very small steps I have to take, like baby steps here. But once I am here, I may be able to take larger step. I may go like here, then when I am here there is really not much changing here. So, I can take larger step, right. But the point you have to think about it is that because I draw this profile here, it is easy for you to visualize it, but this is a chicken and egg problem, right. I do not even know that the system will behave like this. So, how do I know that I need to cut step here and here I can go for a larger step, right. That is why you need an algorithm that will tell you that now you can increase the step size, or nope, keep cutting step, keep cutting step. So, that algorithm is basically the adaptive step size. I will say for an adsorption desorption type of an approach, you must always use an adaptive step size solver. If you use any other solver, it will not, most cases it will work because of the adsorption front and based on the specific adsorbent that you are actually considering. If you have, and we will be talking more about this, I am probably putting the cart in front of the horse here, like going ahead, but I think for our discussion some of these things will be important. One of the things, as you will see, that we will be looking forward is considering something called a breakthrough curve, right. We will be discussing that quite often. These are known as the, okay, I should probably write more clearly. This is the breakthrough curve. This is C over C naught, and this is with time. So, if I have an adsorbent which has got very less kinetic resistance, this guy will become like this, and this will become more elongated except if you have more and more resistance. So, it will be like going like that, right. It will bring more and more elongated. So, if I have something like this, it is actually very difficult without using an adaptive step size solver to really solve this problem. So, how do you actually adapt the step size? So, I need to know that here I do not need much step. At this point I will be taking a lot of steps, so I need to cut steps. Here I really do not need much of the steps. So, one of these approaches that, let us say if I am using an RK method, fourth order Runge-Kutta method, what you can do is that you can do fourth and the fifth order RK method to estimate the local truncation error. Remember my definition here. I define this is the local truncation error, yx at n plus 1 minus yn plus 1, right. So, that is what I actually have a typo, I see this. So, this is actually yn. So, you read it as yn plus 1 minus yn, sorry, this is a typo, I will correct this. So, once again, local truncation error is whatever is the value that I have at n plus 1 minus yn. So that's that local truncation error that I have. So what you really do there is that you apply a fourth order method and a fifth order method, and then you estimate that what is the error that I would have gotten as a result of this with this. If you are using some other method like Euler's method, then what you do is that if I am going for a single step versus I am taking 2 steps, what is the difference of the results? So that just to ensure we are on the same page, say this is the profile I am trying to capture, this is say y with respect to the t, say this is the overall h that I took, like one single step I want here, go here, and I get some result, versus I take 2 steps, h over 2 and h over 2. So this is what is actually being shown in this profile here. So if I am taking 2 steps, say I am taking 1 step, 2 step, this is the result I will get. Instead, if I would have taken 4 steps, this may be the actual result that I would have gotten. If I would have taken 6 steps, this will be here, and if I could take infinite steps, this will be the result here. So what you are saying here is, after certain number of steps, it does not matter. That's the idea that you have, like you take more steps, but beyond certain steps, the difference is not much. So that is what is happening, 2 steps to 4 steps for this particular graphical depiction of what's going on. There is a much difference in the results, but then after that it does not matter much here. So that gives you an estimate of the local truncation error. If that local truncation error is smaller than the tolerance, then you increase h. So what it basically says is that, okay, if I am actually doing this, say I take h over 2, and I take a 1h, and the result I am getting by this is here. So this is the difference, right? I'll show you clearly here. Say this is over h over 2, but when I go here, say this is the result I got. So this is really the difference or the error term. So this small difference is that error term that I am getting here. This tells me if this error is below the tolerance, then I increase the step size. So if this h was say 1 minute, then I will say, okay, let's increase it. Let's make it 2 minutes or 3 minutes or 4 minutes. How much to increase? That's a different thing, and I'll talk about that also. But basically idea is that you need to increase it. If it is below that tolerance, then it basically means that you need to reduce your step size. So all these solvers, like these approaches, if you have used MATLAB before, these things are not available in MATLAB, but you will see in Aspen this option is there. It basically let you know a minimum step size and a maximum step size. This is what it means. So that basically meaning is that as a user you are saying, I cannot let you take more larger step size, but the minimum step size is basically saying you keep cutting as needed till the time that you will not exceed that lower limit, right? Then there are different methods exist on how to adapt based on the truncation error. As I said, I am not actually going too much onto it, but one of the method is known as the Richardson extrapolation method with Berlitz-Stewart method here. This basically actually approximate using a local model. So it is basically fit a local model with respect to the number of steps versus the truncation error, and that local model is used to predict if I am actually increasing the step size or decreasing the step size, what is expected to happen with respect to my error term, and that's how it actually keeps adjusting it. So once again, the takeaway message from this slide is that for adsorption system simulation, especially when you have a steep breakthrough curve like that. Adaptive solver is absolutely critical for you to have success. Even within the adaptive step size solver, there will be two things there. Just to ensure from this algorithmic point we understand it, one is the minimum step size, another is the maximum step size. What it basically means is that if the truncation error is higher, then I am saying decrease h, but I cannot just keep decreasing h infinitely. There is a place where I have to stop. That is, it will stop at the lower limit that you specified. So, say I specify the lower limit to be 1 minute. So, first I take a step of 5 minutes, it did not work, keep cutting, 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 and then it will not cut below 1 minute. So, if it cannot solve at 1 minute, it will basically say sorry, convergence failure. On the other hand, if you satisfy the local truncation error and you increase the step size, which you want to do here, right, then what will happen is at some point it has to stop. So, whatever upper limit you provided, like 5 minutes or 6 minutes or 10 minutes or whatever you provided, it will not let it go beyond that. So, this is how this thing is done. I will stop here for a moment and see anybody has any questions for me. This is an important two things which I discussed, multi-step and adaptive step size. So, both concepts I want to ensure that is clear, because you will face convergence failure, have convergence failure. That is the reality. You should. I will be very surprised if nobody has convergence failure. And that is where our knowledge comes in, and this is where our understanding is important. Mathematically, what is happening, what is blocking us, and how it is happening. So, any questions here, please?
Sir, how do you
Yeah, whoever, it doesn't matter.
how do you decide the tolerance? Do you have any idea how much error will accumulate at the end of all time steps or something?
So, I will show you where the tolerances are there. So, Aspen by default, I think it is 1e minus 7 is the tolerances that is actually specified for these ones, but as an user you can actually cut those tolerances, and most cases, many cases what we generally do is we do actually a sensitivity study. Many cases what you will find is that it's probably one of these places there will be little differences, after that it will make no differences. You can do a sensitivity study with respect to your tolerance. Many times with a very small tolerance you take many more steps, but the results are very little different actually. Yeah, there is no sanctity about telling a tolerance how much it should be, but below 1e minus 3, like normalized values, would not recommended, but 1e minus 5 is actually very standard, but you can go definitely go higher. Yes.
Actually, I have a question, sir.
Okay.
Is there any rule of thumb if you wanted to actually increase the tolerance?
So, the way you have to really see it, and I will talk more about it, is that how these tolerances are actually defined. And there are a bunch of tolerances in Aspen, you will see many tolerances. So, as you know, and for equation solvers we have got many tolerances. One is the relative changes in the variables, like when I am taking a Newton step, I am basically saying xk plus 1 minus xk over xk. That is the relative differences I am saying there. The other thing is that about the equation tolerances. So, the error I am getting the same thing, epsilon, which is the equation error, and then that is basically I am saying those subsequent steps, and then I am normalizing it. Question is that what does that tolerance really mean for you? I will be talking more about this because the scaling is important, and you can sometimes we actually do not care about that. Like for example, if I am writing an equation, just I will give you a quick example, and then when I come to SEM I will give you an example more clearly here. For this particular example, I will go to this this particular equation, I write it like this. Anybody tells me what is the unit of this would be? Any of these terms, like for dimensional consistency, our unit should be same, right? So say rho kg per meter cube, Cp kilojoule kg degree centigrade, this is degree centigrade, and this is second or minute or whatever, right? That is what we get it here. Degree centigrade goes there. So kilojoule per meter cube second. This guy is kilowatt. This is kilowatt per meter cube, right? If I would have written these equations in terms, instead of writing these in terms of kilojoule, assume that I wrote it in terms of joule. This becomes watt. I could have also written in terms of megajoule, and this will become megawatt. So you see the same equation. When I'm trying to solve, I will get different error there. If I'm doing it in the, if my actual error in the solution is simply, say, just hypothetically, I assume that I'm solving this equation and that error is the equivalent of 1 watt per meter cube, and if I have a tolerance of 1e minus 3, this guy will not solve. If I'm doing it in terms of a kilowatt per meter cube, this will become 0.001. So this is about 1e minus 3, so it will be fine. If I'm doing it in terms of the megawatt, so it will be 1e minus 6 megawatt per meter cube. Yes, it will solve immediately. So you see the unit is very important. So this is something which we always overlook. So Aspen internally, they actually, like if you see Aspen Plus, they actually use gigajoule for many of those things, and it keep a very high tolerance there, because many times these terms are actually notoriously difficult to solve. The other thing everybody has to be very careful, and I'll discuss some of this later on, is the pressure unit. This is the one that kills everybody. Pascal is the SI unit we use. Pascal is a very small unit. Very small unit. Use bar or atmosphere or something that makes sense. Like 10 to the 5 Pascal that you have to go to a bar. Do we really care about 1 Pascal, right? But if the error is 1 Pascal, this guy will keep iterating. But do we really, and from an engineering application, it probably doesn't matter. So one thing which is important is actually your units, and I will be discussing today in the afternoon. I will always recommend to normalize the equations and variables so that the result that you get actually is meaningful. So if you keep everything between 0 to 1, there are techniques by which you can do it. So you will never write an equation like this. I would never write an equation like this, because this becomes actually, it all depends upon the units that I'm actually considering it here. So simply think about it. If I have an equation y minus x is equal to whatever, say 0. This is an equation I'm solving. The same equation I can write y minus x minus 1 equal to 0. They are mathematically equivalent, they are not numerically equivalent. I'm normalizing it. This is actually 1. So this, with respect to this, I assume that this case, this is 10,000, right? And this guy becomes 999. This error, this will give you 1. And this guy will, oh yeah, 1e minus 3. You will keep iterating. It will never solve. But if I actually do this, I'm simply dividing 10,000 with 9999. One of you can actually find it out what this error will be. I think this will be like 0.0001 or something like that, which basically tells you that this is close enough. I can say this is perfect with me. I'll be discussing some of these, but remember, when you code, you never should code the equation, never. You have to think about the coding. Before you start coding anything, write equation, derive equation first, understand what it is. But then when you go to the coding, you have to think. how to code it, make it well posed and things like that. So yeah, any other question?
Why can't we normal, like non-dimensionalize it like we do the Navier-Stokes equation?
That's what I actually be talking about. That will not only non-dimensionalize it, sometimes it actually becomes a bit difficult and you have to think through it. So when you non-dimensionalize it, even then the question is that are they scaled between 0 to 1, because otherwise the tolerances are being applied across the board to everybody. So it may be only certain equation that is causing trouble, and those are not scaled. But all equations are important to you, the same importance, right? All equations we have same importance. So I will be, if I'm actually normalizing them, that basically means it's a fair game for all equations. It's not like that pressure drop unit, because I did it in Pascal, that's the equation that always keeps popping up because it cannot solve it. But I decided to do my energy in terms of gigawatt or megawatt, and I can easily solve it. That's not a fair comparison, right? So I'm solving one equation to very high accuracy, but other one I'm neglecting. So those are other tricks that which we need to think about. Okay, any other question here? That I'm actually using it. After that, it goes to a nonlinear solver. So remember once again, this is the type of equation you are getting, or these are the type of the equation you are getting. So the moment you get this, it becomes an algebraic equation. That is why I was telling yesterday that even in the computer simulation, we are always doing a discrete time simulation, because this is based on the step size, how you are approximating it, how you are calculating the step sizes and all of that. But first approach there, remember I said there in that there was the first step is that you have to solve for the step size was, so this was the equation that I wrote. F of xk pk is equal to minus f of xk, right? Remember that was the equation. So this is a matrix equation n by n. This is the guy that takes most of the time. So linear equation solver takes most of the time, depending on how gigantic your system is. So if you are saying I have got 10 million by 10 million, this is a 10 million by 10 million matrix. In previous generations, like most of these computers will actually run out of memory actually to do these things. So they do a lot of decompositions behind the scene and say, this is, can I handle this size? Can I make it chunks and all of those things? That's the power of the linear equation solver behind the scene, because it actually doing all of those things behind the scene to see, do I need to solve this 10,000 by 10,000, or can I separate it based on like 1,000 by 1,000, this 1,000, this 2,000 by 2,000, and then I combine those things. So that's what the linear equation solver does. So that is the guy, takes a lot of time. Once it is done, the first thing is that if the linear solver cannot converge, so remember I was telling yesterday that when the linear solver may not converge, like when say it is doing an LU factorization, or it is doing an LDU factorization, or it is doing another common method is the Kolesky factorization, QR factorization. So one of those methods from the linear algebra class you might remember, once we do that decompositions, it may immediately tell this is ill-posed. Like I said, the diagonal elements shows up as 0 in the LU, you are in trouble actually, okay? So once it finds that, it basically say, well, sorry, I could not converge it. So linear equation solver itself might say, I cannot converge. Then the first thing it says that is h, the time step, is still higher than the limit that you set. So say it was trying to take a step of 5 minutes, then it basically says, sorry, with the 5 minutes I could not solve. Let me try a lower value, but did you set the lower limit at 5 minutes itself? Then I have nowhere to go. If you set that lower limit to say 1 minute, then it basically say, okay, I tried for 5 minutes, I could not solve, it's okay, let me cut steps. So in Aspen, it generally cuts step by half. So if it is 5 minutes, it will go for 2.5 minutes. So then it will cut step, and then it will come back through this route again. If the linear equation solver goes through, then it will go to the backtracking line search or a similar method. There are some variants. I just kept it as a simple things. We need probably bunch of classes to go over these numerical methods things. So I just make it simple. Don't take it in the face value of it. It's actually more involved than as I mentioned over here. But think about a backtracking line search that we discussed yesterday. Remember, in the backtracking line search, one of the things, as I mentioned there, is that it keeps cutting the alpha k lower and lower. If the alpha k value becomes lower than certain value, that means I'm not making any progress at all. Wherever I am, I'm exactly at that point. So in that case, it will come here and it will basically find out that if that alpha k is below some small value, that means I'm not making any progress. At that point, it will basically come back here and say, can I cut the step size? And if the answer is yes, you are still not reached the low point of step size, then you will cut step and go here. If it has converged, then it will adapt the step size. Now remember how to adapt the step size, I mentioned there, that adaptive step solver there. So it will then go to that algorithm and basically find out the local truncation error, and it basically says, should I increase it? I took a step of 1 minute, can I make it 3 minutes, or can I make it 4 minutes? So then we'll adapt the step size and go back. And this is the approach that actually it keeps going. Is it the, I'm not sure, we are probably done, it's 1, right? Yeah, that's why I saw the lunch. Maybe I'll take another 5 minutes, and then after the lunch, I'll continue with this one and then go there. So this is the overall approach. Anybody has any questions about this thought? I decided to draw a simple cartoon here. Behind the scene, actually, many steps are involved there, but this gives you an overall idea. Any question? Yes. So there is something which we can draw from the CFD literature, which always does these things very routinely. And one of the things is something called a grid sensitivity study. So if you say n equal to 20, and I got some solution, so I say y equal to t. So this would be one of the key performance measure. And for the adsorption, the key performance measure is the breakthrough curve. So say with this, I'm getting this profile. Then what I do is n equal to 25. Maybe this becomes my new breakthrough curve. Then I say, oh yeah, I have a lot of error here. This is not acceptable to me. Then I go to n equal to 30. And this might be something very closer to here, and you will say, okay, this looks closer to me, so let me stick to n equal to 25. This is a standard approach to do the grid by doing the grid sensitivity study. Yeah, it's very difficult for the spatial domain to say, foresee and project how it might happen. Time domain possible. Spatial domain is much more complicated to project. Okay. One thing is I wanted to kind of finish it over here is that initial condition is very important for all of us to consider there. At t equal to 0, I have all the variables in the bed. What should be their value? What is the concentration of each of the species there? So if I have a bed like this, question is I said the dci dt equal to whatever, dt equal to whatever, and all of those things. So I have to find out these for each of the location, right? each locations I have to say what are the initial value of all time derivative values should be provided. This is the case with a dynamic simulation, is the initial state there. So what is the initial state? It is okay for many systems to consider the initial state to be steady state condition. This type of variables are denoted in Aspen custom modeler as rate initial. If you declare a time derivative as a rate initial, Aspen will try to solve for a steady state. Can we apply this for adsorption system? No, because it has no steady state, right? So there is no way we can actually apply such kind of a scheme. This is really the trickiest thing for adsorption. We do not know what is the initial state. So you have to go for some simplicity, and that will be future discussion we'll have. So you can say, okay, I can consider the initial state to be when it is fully dissolved. So there is no loading there, and the concentrations everywhere is actually at the inlet concentrations and so on. That's the best guess you can do, right? And that's okay. And I will talk more tomorrow about for adsorption systems. But if you are doing a PFR, if you are doing an CSTR, which has a steady state, this rate initial is a wonderful option. Do not confuse initial condition with initial guess. Initial guess is needed only for algebraic variables. This is with respect to the Newton solver, because remember we always discuss that Newton solver need an initial guess, right? Newton type of solver, because that is where I'm starting. Those are only needed for algebraic variables. So Aspen, when you have give the numbers, it knows what type it is. So whatever is the differential variables, for those it will take those as initial value. Whatever is the algebraic variables, it will consider those as the initial guess for that one. So we'll talk about that more. One thing I like to say and finish it over here is that we generally prefer a step-by-step initialization procedure. The idea is that if I am solving a plug flow reactor and non-isothermal model, I can first solve a model which has got no reaction and it is isothermal, right? It's an easy solution. Then use that solution as the initial guess for when the reaction is turned on. When we use the turn on the reactions, this will be, we can use a homotopy based methods. So remember, you have done probably homotopy based continuation, and you have a continuation parameter there, and then you can slowly crank on the reactions there, and then you have solved everything, but it's still isothermal. Then you turn it to non-isothermal, and then you solve for it. So this writing this initialization routine is actually important for some of the trickiest model. Many of you who have actually used Aspen Plus, and you think actually you drag and drop a box there and block there and click and it runs button, and it works. Why? Because Aspen has done all of these things. They normalize all their things at the boundary. They have an internal solution routine that they have done it. But if you are writing your own code, you have to write this initialization routine for yourself, because you have to, there is no way you can get a good initial guess. So this is the way to trick slowly going there, okay? And the trick is that this is really the takeaway message. You can think about what would be a simpler model that can create a good initial guess for the next round of complicated model. Can I separate my model, look at your equations and say, is it okay for me, I can create a good initial guess for these conditions, but temperature, I have no clue how it will be. And because they are coupled, I cannot solve them together, but I can do an isothermal model and then non-isothermal model, and slowly I can actually create good initial guess. So this is something as an user actually you can come up with it. Once you do it, this initialization routine, and I'll show you where Aspen actually gives you the opportunity. it will actually run it behind the scene for you. That is how all the Aspen Plus routines always runs behind the scene. We just don't see that. Okay, so concluding remarks, I will say that we generally use method of lines, and we use one of the implicit numerical integration approach. We have to keep in mind the accuracy versus computational expense. I will always suggest use an adaptive multi-step method. Now you understand what is adaptive multi-step method means. Then other thing which I did not mention here is anybody who is interested in optimization, because this is a dynamic optimization problem, the preferred approach is orthogonal collocation on finite elements. So something called an OCFE, even any of you have been exposed there. Professor Sachin Patwardhan from IIT Mumbai has got a nice NPTEL video that I also refer my students to. Very nice actually, excellent explanations and show step by step. If you want to learn it from there. Aspen does not have an OCFE implementation, but if you use Python, it has an Pymo has got an OCFE implementations with many of the collocation based methods that you could actually use. For adsorption, we generally use the Redau based collocation methods. It generally works fine. This will be for dynamic optimization. This converts the whole thing into algebraic model, and then it will actually optimize the whole thing. Okay, but I will not spend much time onto this one. We need to carefully decide the initial conditions for the differential variables, and the takeaway message is do not get confused this with the initial guess. They are completely different thing. Okay, I think lunch is ready, everybody is hungry, and what I will do is I will come back and then take the questions, if that makes sense to you all. Okay, very good, thanks. Enjoy the lunch. Any question for that one, but
I'm checking the comments.
okay, okay, that's it.
Also in WhatsApp, their group is there.
Okay.
In case any issues, they are asking.
Okay. That's it. That's it. Mostly everybody is here, right? All right.
Good afternoon, everyone. Welcome back to our next session, that is tutorial 1 by Dr. Devanshu. He will cover the Aspen software basics and also the Aspen custom modeler. Please continue.
All right. Okay. Thank you. Already. Oh, let me quickly check. Okay. Yeah, I think it should be understood, understandable here, but I will. Yeah, I see some things got moved, but that's okay. So the first thing I would like to discuss today is that there are 3 softwares and people interchangeably use it. One is just exactly, it's just basically saying that they built some of the models for you. That is only the difference in Aspen adoption. We'll be talking more about these fixed spread adsorber model, like that will be day after tomorrow, where we'll talk about that. It has a library model that has got the balance of plant, such as heat exchanger valves, etc., that you can utilize it. So that's the only thing there. And the other thing is that if you want to use any other models there, because it is built on Aspen custom modeler, you can write your model and then you connect it. So if you want to use a moving bed or a bubbling fluidized bed or any other bed, you can connect it there, right? And we'll be covering Aspen adoption more in later, okay?
PPT convert చేసే PPT excellent.
Oh, okay.
So Devanshu, just 1 minute. He's adjusting the slides.
Switch audio. This one is fine.
They ran animation, right?
It should be fine. Right. That's so fine. Yeah, looks good. Yeah, thank you. All right. I will not discuss this slide, but if you're using GPROMs, we can discuss separately. Okay, so what do we have here? Like this software actually look like this. So let's see, we become a little bit familiar with it. So when you use Aspen AdSim, this is what you will also see, right? So what it is that this is basically the help. So you can click help, you can get this. This is something called a mode, like it shows steady state. You can run it for dynamic or anything. So when you are running Aspen Adsorption, it will always be a dynamic mode over here. This is the run control toolbar. So this has got a bunch of things like a run and stop and pause and go back and all those kind of options. Then this side, you have got everything else, like all items pane, and we'll discuss more about it. This portion is called the Simulation Explorer window. So we can explore what is actually happening here. Then this portion is called, this entire window is the flow sheet window. So this is where you build in. Like for example, if you do Aspen Plus, as you know, this is very good. This is very good. I was just really looking for this one. Okay, wonderful. This makes so much sense, really. So thank you. So flow sheet window is, this is like what you have seen in Aspen Plus, where do we drag and drop. This is exactly the same thing. And then here you will see the status bar, right? This portion is very important. You must keep an eye in this portion. This tells you a lot of things over here, and I will discuss this more. The other place is the simulation message window. That will tell you as it is iterating. This is the window that tells you what the solver is doing. So remember that when you, as I keep saying, that you will always have a convergence failure. I will be surprised if you don't have. You're just lucky. But most cases you will have a convergence failure. This message will tell you, this message window is the all that will tell you everything. But by default, they hide actually a lot of those messages. So we'll talk about today that how to have Aspen report or tell you what is the trouble that it is going through and what is the problem, so that you can troubleshoot. As an user, you can provide your ideas there, right? But as you work more onto this, this becomes more clear about this. One thing at the very outset I would like to mention here, and this is the main and the one of the key thing here. If you just drag and drop, like you built a model and you drag and drop over here, it will grab all the equations from that model, but there could be additional equations here that it is also grabbing. So we have to know that from where it is grabbing additional equations. So I'll talk about that. So like this is the main, one of the main confusing thing with Aspen Custom Modeler. If you have an Aspen Plus and you drag and drop boxes, it's pretty straightforward, because you kind of think like, okay, whatever it is I'm seeing it in the flow sheet window, those are the only equations being generated, not in Aspen Custom Modeler. It will take things from here. It will also take things from here. From where? We'll talk about that. And then it will combine everything. You do not have to worry about it. It will look for equations wherever you have specified. It will then combine everything, and then it will solve for it. Okay? Any questions anybody has here? We'll go over each one of them in more details, but this is the overall look and feel that you can have. If you have not opened yet, I would say that if you all can open, that way we can test it that it is working for you. So this should be shown up under Aspen Plus. So open up Aspen Custom Modeler. It will be probably easy for you to follow along with me here. So again, I'm actually opening it over here. if you see, it will be under Aspen Plus, okay, and here you will see Aspen Custom Modeler. So please do open it because you will be working extensively and it will be easy for you to follow along. So if you open the Aspen Custom Modeler here and it just opens up. So this is exactly what I was talking about. This is how it will show up. Did it open up for everybody? Anybody? Okay, okay, good. I always keep forgetting. This one shows you. Okay. Very good. Okay, so the side here, again, look into your portion that you have opened here. If you click on this thing called flow sheet, okay. If you just keep it on, look into the flow sheet, you will not see anything here, these blocks and everything you will not see. Do not worry about it because you have not built anything here yet. But when you will block, you will have created, it will populate it, all of these, okay. This one, when you actually open it, anything over here, all of these blocks are, you have actually placed over there. When you look into the flow sheet under the blocks, that will show you the block, but below here in the contents of the flow sheet, look it for this particular icon. If you see this icon there, and if you click on that icon, just click on that icon, it will open up this additional box. Right? If anybody, for anybody it doesn't work, just let us know so that we can help you to troubleshoot. What you do here is that here you can write your own equations. So if you are using Aspen AddSim and you want to write your own equations, like something else you want to do, and you say, I want to do some economic calculation as part of these ones. I also have a bunch of other additional equipment items and all of that, and I want to write those model equations. You can either create a block or you can write those constraint equation inside here. So when Aspen works, what it will do is that whatever is in your flow sheet, like in this all the boxes and blocks you have, it will grab all the equations as part of these constraints also along with it, and together it will solve. You don't have to worry about it at all, that saying, is it seeing that one? No, it is always looking for that. If you keep it blank, well, say there is no equation here, but otherwise it will always look for this window to see is there any equation here and combine it. There is another tab called Custom tab over here. This Customs tab is the place you will be working on today. So we'll be writing all the models, this Custom tab where you will see a lot of things that will happen. We'll have the custom model, ports, variable types, and I'll go over that in a moment. Then you have the libraries. These are the libraries that are there in Aspen, already in Aspen Custom Modeler. Remember, some of the libraries here are actually also in Aspen Plus. In fact, this is interesting. I'm not sure how many of you in Aspen Plus have come across a reaction kinetics and you kept thinking, oh, there is no way with the inbuilt reactions model I can model it, right? This is a tool. You can create a model, a reaction model in Aspen Custom Modeler, get it as a library model to Aspen Plus. It will seamlessly work actually. Any model you develop here, you can also make that in Aspen Plus library model, and then you can add to the Aspen Plus model library. This is your own library, so any model that you do not have in Aspen Plus, this is the way to create it and take it there. So it gives you all of flexibility. This library gives you a lot of options, and I will go over each one of them. These are the pre-built model and then many variable types that exist there. Okay, any questions so far? Okay, so keep following along with me as I am going through this window so that it becomes clear to you. Now we'll be going details into each one of them. So first is the custom model, right? You have not built a model here yet, but let's say if I build a model here, this is how it will actually show up. So if you build a model and then you click on your model, it will show you all of these icons over here. So it is basically saying for Aspen, the model is not a model. The model has got many other things maybe associated with it, and you can get a lot of association with those models. So let's see what is there in the model. So if you just simply look into the model, this guy, if you click, it will give you the model itself. It's only the equations, but at the top of it there may be other contents. Like for example, this particular one, it's a initialization 1, 2. Remember I was saying that many cases initialization is an important thing. I can write bunch of initialization. So these ones I can just actually double click and it will run that initialization script. This sits actually at the top of the model. So it will solve the model, grab a portion of the model and keep running it. So everything, all of these things you can create it, and you see it gives you a lot of things like icon 1, loading, there are maybe additional plot that you can generate and additional variables that you can generate and all of those stuff. So we'll look into this more later ones. You can also create, this is very common, like the tables and the plots. You basically say, I'm really for my paper that I'm writing or for my project that I'm working on, I just only want to focus on these particular variables. You can create the tables here, plot here, and then when you run it, this table is already created, the plot is already created. You just drag and drop and your paper is ready. So those type of things you can actually create it here. This is inside here. You can also write scripts and tasks, and I'll go over this a little bit in more details in later ones. And then also the model icon. If you don't like it, the model icon, they have a default model icon. If you want to have a very fancy icon, you can draw, drag and drop, and you can even get a JPEG or something, and you can do those things. This is the main Windows stuff, like as you know that we have always done that. And I have said the run mode here, you can actually click onto this. If you have open Aspen SEM in front of you, I will say click onto it and do check this, because this will be our kind of a bread and butter all the time. These are the different run mode that we need to consider there. This part is the simulation controls here, and this is the main place where you really need to look into when things do not work as planned, which it will, right? So when you have a convergence failure, you have issues there, this is the place where all the settings are done, and we'll spend a lot of time on that, okay? And then here is one interesting thing is the snapshot. So I was always saying that you need to create an initial guess. So anytime you have a luck, anytime you have a luck in getting a good convergence, you can simply create a snapshot. So you basically say, I want a snap. Snap is just like the word of it, like I'm taking a picture of it. So what it does is that it will take, it actually does a lot of interesting things very beautifully. It will grab all the specifications of all variables, and it will also grab their current value. So it is initial guess does not mean that, like snap does not mean that it is only grabbing those values. It will also grab their specifications, like if a variable is fixed and whatever. So those specifications also it will capture. So it's in some sense where you are right now, it actually snaps it. So in many cases what happens is you will actually create a lot of snaps there. Anytime you have a luck in converging, you say, oh, this is a good model, I don't want to lose it, let me take a snap. So next morning you come in and you can start from there. So remember what I was saying, that you sometimes have to slowly go one step at a time using the solution from the previous case as an initial guess. So that snapshot is the tool that will help you to do that. Anybody has any questions so far? Okay. Setting up, now we'll do the steady state model, right, with a simple example. So this is our hands-on stuff. I've already gone over these equations and we'll be doing the simple CSTR model. So this is set to 0. That's the model we want to do it. So first thing, let's all work together. You need to set up the properties. So for doing that, because all of you have open here, so let's work together. Come to the component list and then click configure properties. Anybody has trouble, let me know, raise your hand. So it is on this Explorer window, click component list. This will give you a drop option here and then click configure properties. Just raise your hand and we will be coming over to help if it does not work for you. And what you need to do is that once you are done, then you click this button called edit using Aspen properties. That icon you have there. The moment you click that, it will open up Aspen properties. Did it work for you guys? Okay. Anybody whom it did not work? Okay. I did not see any hand here, so let's go forward. Once you do that, then let's type in these ones. Not open for you? It's just slow. Okay. You have the slowest machine, sorry. Oh, oh, okay. I see that we have the lot of helping hand here. So if it opened for you, go ahead and there you need to provide this under the components specifications. All these components you need to insert. If you do not know how to insert, it will help you. It will actually open up a box. Just simply type the number. If you say methanol or acetic acid or methyl acetate, it will automatically find it out for you. Edit using Aspen properties. So, so if you see my screen over here, so we did the component list, right? And we did configure properties, then select this, okay? And then you say edit using Aspen properties. So far so good, everybody got that? And then here you can actually just simply type in, these are simple components. So if you simply type methanol, and once you type it, just simply hit enter, it will populate it. For some complicated one, or you want to give a different name and all of that, you will see that my names are probably a little bit different, but it does not matter here. You have to go under the find. Sometimes you are not sure about your component may not be so simple and you get confused and say, okay, this, let me search for it. Then here you will have to give this and then say begins, contents, equals. If I say contents, right, and if I type methanol, every component that has got methanol, it will populate here, and I don't want it, like I'll show you. If I say methanol, right, and I had the set contents and say find now, you will see all of these components that is in the database it is pulling, you see. everything is in some sense has all of those, right? All these components for which it has got the thing. It actually gives you, sometimes it is good because it gives you a lot of other things. It gives you the which data bank that it is it is grabbing the properties. So it is saying I'm getting it from NIST data bank, because Aspen properties has got TDE, or the what we call the thermo data engine, TDE. So it is pulling it from here. It gives you the cache number and all of that stuff. And then if I do it equal, then it is easy. It will just give you only methanol. So if you are going by this route, this is fine. In that case, you just select it and you simply say add selected component. So there are two ways to add components here. You just type in, it will automatically populate and you look for it, or you come here and here you type it and you check it out yourself saying, yeah, this is the component I was looking for, and I can say add selected component. See, there are two of them. I do not need that because one of them I just did that. I can just select it and I say delete row. You say, do you want to delete the row? You say yes. Okay, so with that, what is, sorry, is it background? Okay, all right. So ensure that you have these, and remember the name is the how it is that you can actually give it the name whichever it is. So ensure that everybody has these ones. Once you have that, then you will get under the methods and the specifications. So we say methods and the specification and select Peng Robinson for this one. Right. Did you get the slides? I actually, in the email, perhaps that may be easier. Yeah, I was anticipating. Yeah, so that's why actually you have to say equal to, and this one will be good actually. So I just want to ensure everybody could enter the names, and if it is not, just raise your hand. Once you are done, then go to the methods, then Peng Robinson, and then once you do that, it will show you the parameters as red. Remember that ID that you have there, you can just change it to whatever you wanted to, right? That's just a typeable thing here. Like whatever you have here, you can just type it to whatever you wanted. Already, everybody, is there anybody who has issues? Please raise your hand. I can just quickly come over to see is it good. Okay, you're typing it. Okay, I think. Oh. No, that one is a problem. You have to probably use another machine, I'm guessing.
No problem, I will follow you.
Right, but I will. You're good?
Yes, sir.
Okay, you're good? Good. You're good? You're good?
Not done. Just stuck here.
Okay.
Just need a head.
I will say if you have the PowerPoint that they wishing you're good, you guys are good. You're good? All right. You're good. Yeah, this machine is the only one that troubleshoot. So remember, like this side of the name here is just arbitrary. We just provided some name here, but it is methanol, acetic acid, methyl acetate, and water. When I went there, I saw the resolutions of the screen is not good. So please open the PowerPoint presentation. It should be in your email actually. So please open the PowerPoint presentation and then use it from there. But you do not want to lose any of you here actually. So if you had stuck, just raise your hand. Okay, so once you have that, then you do the Ping-Robinson, and then once you have that, you will see that it has the parameters. This icon becomes red, and you just need to click on that one, and it will show you the binary interaction parameters there, and you just accept it because it will automatically become green. It basically wants you to show that I'm dragging the data points from here. Are you okay with it? That's the only thing it is confirming, right? Once you do that, this thing will be gone. Once you have that, then I will say that export these as a document. So under the file, export a document, and save as Aspen properties problem definition file. You will see there is an option called APR PDF.
After that, sir, we selected all
Yeah,
the four.
right, and then if you come to the parameter, just double click. Yeah, double click and say binary interaction.
Okay.
And then click on this one.
Red one.
Yeah,
Okay, sir.
and so it is gone. So it is happy now. And now what you do is file, export, and then file export document. Yes, and then you save as you are given as APR PDF. There are other options that will also work, but I will suggest just to be consistent, use the APR PDF. There are other options that will also work, but do it as an APR PDF. So this will create a file which is separate. You can load it at any point of time. Sorry? It will actually create that one, and you can embed it. That's why you can save it and go out. No. Yeah, folder with your name actually. Yeah, so let's see. Yeah. So, yeah. So you come to methods, and here you have to show the whatever is the Ping-Robinson. They suggested. Where is the Ping-Robinson? Yeah. The moment you do it, parameters, it becomes red. It basically saying I am dragging these parameters from here. Are you happy? So that's what it wanted to show you. So it's basically required include complete. Then what is a file export, and in your APR PDF. So this is the one problem definition file, and give it a name like and save it there. That way, that's a separate file actually. Yes. Yeah, do not worry about that. It does not. No, I said APR PDF actually. PDF. So if I give, yeah. Do not do the BKP, APR PDF. So if I click it here, so if I say why it is still, no, here you have to actually select it. So Payne Robinson here, okay, and then it comes here and it says, okay, this is red. Why it is still here? What are the components that you have here? That's strange. But if I say it already have it here, but it was somehow complaining about that. So it is okay now. It was just somehow the red button was not working. So now if I say actually I say do it as a PDF. Okay.
And on desktop, sir?
I'm not sure. Yeah, whatever folder. Just select the folder. Yeah. Yeah. So please do create a folder with your name so that you can grab that one, okay? So I'm guessing everybody is good here? Okay, so then next what you have it that if it did not work for you, you can use some other, use this file also, we shared it with you in that email. If it did not work, you can just import that file. Generally, if you are taking our file, then basically the way to do it here is there is an import option. So you go to that import option, and then this is the file that you have over there. Okay. Once you have that, you click on the default. So once you have the file, it will show you a green box, and then you are done with it. So I guess everybody created their own file, right? So you don't need our file, that file that we shared with you. If it, so you should not be, no, you should have a PDF option. Oh, you have already done it, but basically in that case, what you need to do, you are good, and then you just come to the default, right? All of those things. The component list. So select it, move it on this side. So click on this one. Okay. If you click the default, it will show you those 4 components that you already put there. Select all those 4 components, click here so that this is on this side. So the thing is that you can actually create a lot of those, but you may decide not to use it actually. So, oh, yeah, it's not going here yet. So if you have to click it in the methods, then you have to go to the parameters. There's a binary interaction, and now it is done. So you see, now it is done. Okay. Then from here, you can simply say export file, and then you say I want to do the PDF. Which we had saved, sir, like this now. Okay, that is good, and that is fine. So you can do it as another one, but you can just actually close it now. Okay, if you close it, yeah, and you say okay, you do not need to do this. Then once it is done, what is your Aspen custom modeler here, right? So you see this becomes green actually. Okay, then you simply say okay, and then if you come to default, now you have all of those. So select these, all of these, and then push this. It will go to the other side. Right click on double click on this one. It is from this one, and then you say yes. It again goes to. So if you create edit using Aspen properties. Yeah, you have that. Yeah, so go back there. Can I see it? So no, so you have gotten. So you have all of those. So what I was saying was that just select each one of them. So you should be able to select all of these and then push it on this side. And then simply say okay. Yeah, that's up to what we need to do. Anybody who is stuck with this step? You don't have to save that. Yeah, you simply say no. Yeah. Oh. Yeah. So then just select it and click this. It will go to this side. Very good. Yeah, I think your machine got hang, I think. You are good? Everybody is good here. Huh? Oh. We are still getting the same problem. Okay, so if I come to configure properties, I need this. You have it. So now what you do it is come to the methods and then you go here and then you select, like I was saying ping Robinson, but you can use others too. So do ping Robinson. So then it becomes red here, so parameters, then binary interaction, and it is happy. So required include complete. And I was saying just do it and then you say export, file export, and here you say API PDF, you say save, and then once you are done with it, you just close it. Okay, you say save changes, you say yes, and say no. Yeah. So now it is green, so it is saying I'm happy with it, and then you say okay. And then once you have this, then it will show this. So now you select all of those, and then push it. It says okay. So then basically saying yes, I want to use it. So I'm actually on that state right now. Okay. Is there anybody still have any issues? Okay.
Sir, we opened the file. It showed that there are 4 errors. This way it came. We just import करने से नहीं हो रहा था. We selected open, and then from the location.
No, you already embedded it. Can I see it for a second?
This was the file I said.
Did not you embed? Oh no.
That time.
No, it is incomplete. It is doing it because this is not. Oh no, hold on for a second. This place should be green. No, you do not have the component actually here. Did you see already created here? Is this the one that you did, right?
Yeah, this is there. I saved down the in the desktop also.
Yes. That file was probably not saved somehow, which I cannot say. Because your machine seems like this is giving a machine language actually. I will suggest you close this and come back again.
To create another one.
Yeah.
Same I got, sir.
This is almost seems like giving you a machine language error. Okay, so what I will do, I will quickly show you. I think most of you got it, but for some it did not work. So I will just quickly once again show you that what happens here. So So I do not remember what it is, but I just show you for 2 components and you can follow the others. You have the presentation. So if I have the H2O and methanol, these are the only 2 components I consider here. Remember what I was actually saying, I can name it anything. This is all depends on me. If it is convenient to call the water something else, I can just call it something else. I just say what. This part is my ease that I want to do. Like for example, it simply rename. Simply the same thing here, we renamed it as MEOH like that. So this is, it basically says, do you want to do rename? I say yes, do rename. Once you are done with that, then next step is go to the methods. Okay. Under the methods, you go to Ping Robinson here, and then the moment you do this, these parameters will be red because it does not. And then if you double click, it will be gone. So it basically say, I am getting the parameter here, are you happy with it? Or check it out, so that it is not doing behind the scene that you do not know. And we all know the Peng Robinson, like PR, BAB, these are the parameters. So this is drawing those parameters here. Once you are done with this, what I was saying was that this is not necessary, but you can do it as a file, export, and you say a APR PDF. What it actually does is that it creates a separate file for you. Anytime you want to import in the future, it is helpful, but otherwise it is not necessary. I just simply say, yeah, I said I already have that. Error accessing file. That is interesting. Yeah. Such time was okay. That's interesting. Okay, let me see, I already have it over there or not. It's here. So the main thing that you need to look into here is this green box. If you don't get this green box, there is something wrong. So if I have the green box and I simply say use edit using Aspen properties, it will open up the correct file for me. So see, it is already here. So even though I had that trouble, but generally if you do not want to save that separate file, you can just come to the close here and that's it, and it will be fine. It is embedding it within this system. It is just embedded. I just created the properties file separately, but that step is not necessary. Once it is there, you come to OK, and then you come to default, and these are the components you have. So you select that and click this one, it will go here, and then you say OK. Did up to this work for everybody? Is there somebody for which it did not work? Okay. So the next step that what we want to work on is the following. Okay. You come to here called custom modeling model, and then click add model. So here custom modeling model, then click add model, and then you can double click onto here and then give a name. I name it as CSTR because we want to do a CSTR model, but it's up to you whatever you name it. If for any of you the properties file did not work, just grab the properties file we sent you in the email actually. You should be able to import that properties file and it should work. So next step is to create the model. So once you double click the model and you say add the model, give a name called CSTR. Anybody for whom it did not work? Yeah, name CSTR. We're good? Okay. So the next step is what we want to do. Once you do this, this will actually, you will see the model itself. Here, it tells you that how everything is actually declared and what are the different types you have. So it will create a template for you, and that will have everything here. So if you open it, did everybody open it up? Okay. So the next step is we have to write the equations inside it. So for now, there are 4 things that we will be looking into. One is variable, second is ports, third is equations, fourth is the properties call, right? These are the 4 things we want to do. So you must declare all variables with a type, and so many different types are also available in the here. You can look into, like, if you really want to see, okay, what does it mean by variable types, you can look into their library and variable types, and it will give you all kind of variables that it has. So why does a variable type matters? It is because that with each variable type, it brings in a default unit, and it brings in a low value, low limit and upper limit. That actually helps you for simulation. It keeps it constrained within those limits. Those are by default. So if you would say this is time, or this is temperature, or this is pressure, it automatically brings those type of things. So do declare this as a type, whatever type we want to do. So, this is how it should be actually look like, and we can also do variables and no type. That basically means it's a parameter. It's not a type actually. It's not any variable type. You just simply say as a no type, and if it is a no type, you can actually give a lower value and upper value and whatever. This is up to you, okay? Now the next thing is, this is one important thing. All variables in ACM has an attached units, like that variable types actually does that. However, ACM will not track the units for you. So if you made a dimension mismatch, it will not complain that, oh, there is a dimension mismatch, right? To the best of my knowledge, other than Mathematica, there is no software that does it, even today, that will complain you about that units not working fine. But ACM does not do it. So, but these assigned units, why they are there? There are sometimes it will do an automatic conversion of values to different units for display purposes. Like for example, you say this is in kg, but I am interested in seeing it in gram, or it will make those conversion for you. So those are the things, that is why they have the units there. And then of course, whatever is the default unit at which it will be calculating the properties values, because it is calling the Aspen properties behind the scene, so which we will see. So now what we want to do is declare the variables from our model. These are the different variable types: concentration, temperatures, pressure, reactor volume, reaction rate, rate constant, equilibrium constant, and molar density. Quite a bit of variables over here. So how do we declare that? So there are 2 types of variables. One variable that are indexed variable, like if I go by concentration, this C, you see it is called a component list. That basically means here is that in the component list, if I have got 4 components, it will automatically replace that. So like for example, it is saying, meaning is C methanol, C H2O, C acetic acid, C whatever, right? It will automatically replace for you. Like if there are 20 components, you do not need to write their name. You just simply say component list, and it will automatically create an array of all the variables there. So if there is something like that, you just say that C component list, then you say as, and then this is concentration. So I simply say concentration underscore mole. The same way, If it is not indexed like volume, there is not indexed, you simply say V, which is the variable name. Remember this variable name I gave, you can give any other variable name that you want. You can give volume or VOL or VL or whatever, and then you say this is as, and then this is say volume. That basically tells it what is the variable type. So as, whatever follows after this is known as the variable type. And then in the description, this is all up to you. It is a description, some optional description, you say this is volume or whatever. Sometimes we write a long text so that somebody taking my code understand what I wrote, and then this value and this in number which we provided. So does it require the value here? No, but this is one place to provide your initial guess for any variable. If you type a value over here, Aspen will use this as an initial guess for that particular variable. This case I just showed it here, but it is not needed because the volume will be fixed for this case, because we are doing a CSTR. It's not needed. But if you want to do it for concentrations or anything, this is how you have to write. You have put it in this parenthesis, write the description, and then write a value. Then it will grab that as the initial guess for that particular variable. Okay? Any questions so far? Okay, if no question, go ahead. This is what you really need to do. So I just showed you one where is a single value and then another is a component, and you need to do it for all of them. So concentration I already showed you there, reactor volume I already showed it there. So let's do it for temperature, pressure, reaction rate, rate constant, equilibrium constant, and molar density. You need to declare all these variable types like this. Yes? You should always declare as a type. So if you say there is nothing, you have to say as no type, because otherwise nothing is associated with it. So this is the fundamental difference between coding in MATLAB versus Aspen. Aspen has for every variable there is a lower bound and an upper bound associated with it. Otherwise it will take a default value if you do not do anything, and I cannot remember what it is. I think it is minus something like crazy value, and upper limit is like 10 to the 10 or something. You don't want to do that actually, because that means that any value is acceptable for you, but this will actually constrain you. Like basically you say, well, temperature cannot be 10,000 degrees centigrade, right? So this will actually help you for it to search. So for when a Newton based method, it will help you for convergence. So always declare as a type, right? What type you have. Okay, so if everybody understood, again, please open your PowerPoint presentation. Keep seeing this, because if you cannot see the screen from here, I will say that take the V and the C as an example. So remember, volume is not indexed. Similarly, it is CSTR. Temperature is not indexed. Pressure is not indexed. Then reactor volume, we already showed this. Reaction rate, is it indexed or not? No, there is just only one reaction rate we are concerned. Rate constant, is it indexed? No. Equilibrium constant, it is indexed? No. And then molar density. Molar density? No. It's just one, it's a mixture molar density. It's not like pure component. It's the mixture molar density. So only concentration is indexed. That is why we wrote here for each component, and none of them are indexed. So please go ahead and type temperature, pressure, reactor volume, rate constant, just following this template. If you have trouble, let me know. Yeah, do open up the PowerPoint, please. I see that it's difficult for you to see from there.
tried to open this form. This way it is coming. Okay, already did not do anything.
Yeah, so if you close this, did you restart your machine?
I
Did you?
created the file again.
Excuse me.
Yes. Yeah, go ahead. Is somebody online? Yeah, please go ahead. We can hear you. Go ahead, please.
Sir, I had it down. Yes,
Oh,
sir. I had it down, sir.
Okay.
So, yes, sir. So for all the things, we have to first define the variable types now, sir.
Yes.
So, actually, in my system, it is asking for a scaling value, sir, which is not there in the presentation in the slides that you have uploaded. So, what should we do for the scaling values?
At which step it is asking you the
So when we are entering the lower value, upper value, and the actual value, so there it is also asking for a scaling value.
Oh yeah, you can use a scaling value, but that's not needed. You can just delete that.
Okay.
Yeah, yeah, yeah. Okay. Okay, yeah, thanks. Yeah, please. Yeah, let us know if you have any other questions, okay? This machine, did you restarted it or
I'm starting again, sir. As per the option.
something wrong with these two machines? This is giving you a, yeah, these two, to be honest with you, I do not know. I will say if you can please restart it. This is giving you a machine language error. That error is from machine language. I should not be giving you that. There is something got corrupted somewhere. I just do not know.
We tried opening the file that you have sent also.
Yes, yeah, use that.
Also, the same error is coming.
That's what I'm saying. It's something, restart the machine, please. Yeah, yeah, let's see.
So
You're good?
There is no type called reaction rate, only reaction.
No, that's okay. You can always say no type.
Oh, reaction rate is no type.
You can do as no type. Anything that you cannot find. Okay, so anybody has, okay, good. Okay, you are doing it. Wonderful.
Do like say for example, if you have disappear as highlighted to a blue color, right?
Right.
Like
right.
that, does this come like a no?
No, those other things, the temperature, pressure, volume, it will not do that actually. Anything which is linked to this particular model, that is what it will be doing. That like component list, it is doing the component list here. That's what it actually tries to do. So you are good. Temperature, pressure, volume, all of those. So I will show you all how it actually looks like. Okay, so let me open up the file here. So okay, I'm not sure you can see this, but I will like zoom it. This is how it will actually show up. So as I was saying, the reaction, like for example, the equilibrium constant and parameter I am declaring here as no type. So V as volume, and I already showed that, T as temperature, P as pressure, R as reaction, okay. Kf as no type, you can put R as also no type, Ke as no type, and rho mole as dense mole. Okay, so only these declarations, if you do not know what are the types there, you can always find out those types there under. So remember, the variable types are in the library. Modeler and variable types. So these are the variable types that it supports. If you just do not know and basically say, well, I have no idea whether you have a something called a reaction, this is the place to really see that whether you have something. You see there is something called reaction, you can click onto that and it tells you what it is. It tells you that this is a molar reaction rate. Okay, so up to this place, sorry, I'm not sure you can, you really need some good eyesight here like you, right? You can see it? Oh yeah, you can see it here from here. Are you able to see it? Huh?
What is the type of mole? This will be no type? Molar density?
No, I said dense underscore mole. Underscore mole. Yeah, I'll probably see that how I declared it there. If you are able to read it, yeah.
No, very difficult to read that. I can search it from. Yeah, this one.
Is that the light? Why? We are not able to see it from this distance. That's what I'm seeing it.
No, just now we zoomed it in. Still it is not visible.
You are not able to see still now, right? You can see it, right? You can see? No?
Here?
No,
No.
And we shared the files also, right?
Yeah.
So the zip folder which we shared, right? In the zip folder, this file is also there. You can open.
Yeah, probably we'll ask you to code and probably not copy and paste, but check it out actually. Okay, so let's move on. Yeah, this is pretty good actually. So the next thing that what we want to do is, where is my stuff? It's open somehow. Okay. Okay. So you have already done this, the temperature, pressure, reaction rate, rate constant, equilibrium constant. Now the next thing we'll be doing is the ports, okay. So there are different type of ports that are there. Like this is give you the material flow between unit operations, and we'll be looking into different types, okay. So port, one thing you have to remember is that you can only connect similar ports. So what is coming out from one unit operation, if you want to connect it to another unit operation, outlet port for one and input port for the other one must be the same. Otherwise it cannot connect, because there is an exchange of information through the ports. That is what is important. So in this case, we have got create two ports, one for methanol and acetic acid and another one for the product. So we'll be using the main port type. So this type of port brings in molar flow rate, temperature, pressure, and the mole fraction, right? So this is the type of the port that it will bring in. Yeah. So how do I do that? You come here and you say feed A. So this is the name of the port. So I'm naming the port as feed A, and you say as input. So this is an input because it is saying this is the flow direction as the main port. Same way, you need to create two input port like feed A and feed B, and then there will be one port which will be product. When you do the product, this will be as output. That's the only difference. So you will have a feed A, feed B, and then you will have a product port which will be the output main port. So let's create these 3 ports. So the ports actually bring in information and brings out the information from the system. Is it working for you guys? Still not? Same issue? Huh.
You're not able to follow.
Seems like this whole row has some trouble, this machine. I'll say we have to figure it out before Aspen adds in. Maybe these machines or.
The other people will be sitting there, at least we can know what is happening.
So what is happening with that one? Let's say if you just
You told Mrs. that it should not come. Same is coming again.
so if you go now, go to edit using Aspen properties. Yeah, click that. Right.
This one?
Right, and then click edit. Yes. Now hold on. Now close that one. You need to close this Aspen properties first. Yes. Say no. Okay. Click that. Yeah, if you just do the components now.
Again, creation again, sir.
Right, okay, so just do 2 just to ensure that we are on the same page, and do water. Okay, and say, no. Then you go to the properties, the methods. Methods. Specification, say Payne Robinson. Yeah. Yes, and then click it here. Parameter, click it on the parameters. Yeah, and then binary component. It's all done. So now what you need to do, I say file, export, and the file export a name, and then select it as a
PDF.
PDF, and say save.
We're doing same thing.
Okay. Okay. Let's see. I'll see this now, and then now you close the file, and it'll say save changes. Say yes, and no. Okay. Let's see. It is green. Then you say okay, and then you go to the default. Click the default, and select those and push it on this side. So you just need to add those other 2 components. That's it, and say okay. So you are done with the properties. So you just need, I just showed it for the 2 components, but there are 4. So you just need to bring in additional 2. And yeah, and then have the, do you have the PowerPoint presentation? Perhaps let's open the PowerPoint actually. Yeah, if you can do that, that would be good. PowerPoint tells you that how to declare those variables. You are done? Yes. Good, good. B also input, yes. So A and B are input, and product, the PROD as the output main port, right? So I'll show you here how it will actually look. So feed A as input main port, feed B as input main port, and product prod as output main port. Next, we need to write the equations, okay? So for doing these equations, what you do here is, I just cannot find it where it is. Okay. So for the CSTR, we also need the equation for the rate constant, equilibrium constant, component mass balance, sum of mole fraction, and concentration equation, and molar density equation. So this is the rate constant. So let's write those equations. Kf is equal to, so this is the equation you need to write. So let's write this equation. Kf is equal to this one, and For equilibrium constant, let's write Ke is equal to whatever value you have. So what I'm saying here is, so this one, Kf equal to this and K equal to this. So these two equations please write, because these are the rate constant, right? Equilibrium constant, and this is the forward rate constant. So we just gave it a name. So these are two of our equations. Anybody has trouble in entering these ones? This should be straightforward, this one. You should be able to type it. You can see it from here. Yes, this is good. This is good actually. This is clear. Yes. There's some trouble? What is happening? Oh, you're just emailing? Oh, okay. I think he has to open up that file actually, because we're probably. Okay, that's it. Yeah, very good. Thanks for helping. Yeah. Okay, so we are good here. Anybody has trouble here?
There is no necessary to mention units.
So as I was saying, that it already brings in the unit types, and so it gives with the variable types that you have. And I will show you also some other things that where it is from, it is getting the units actually, right? Because we already declared that. So I will show you that here. So it is actually SI unit by default. It will do it. It will talk about that. So there was a question about the units, and I just want to clarify that we are on the same page from where it is getting the units. So remember that for each of these variables, right, we declared these as a type. So we did is like we said temperature and the pressure, and we say the reaction and the concentration mole and all of that. Like for example, if I go that we say R as reaction, right? That is what we declared there. Now if you, what you will find here is that if I do R as reaction, so I come here as the variable type. So where do you see this? It's in the libraries, modeler. So you can follow along with me. So if you want look into libraries, modeler, and variable types, and under here if you have the reaction, it is basically saying this is the unit by which it is taking. So kilomole per hour meter cube, that is what it is actually taking. By default it will take it. Now you can change those, and that is where we did it in the component list. Perhaps I will show it at another point, sorry, by the default here. And here under the edit, all of these actually shows up under each one of them here. So you can change the units, but you have to just be careful. Those are the default units that it will actually take. And then under the globals also, it gives you all the other global parameters that in this case we did not declare any of those types. Okay, but those variable types already bring in the type of the unit that it is actually expecting for each one of them. Okay, so the next step, I see many of you are already done with this, these two. Then once you declare Kf and Ke, let's write the reaction. Let's say R is equal to Kf times C MEOH times C. If you name it differently, then name it accordingly, please. So these are the reaction rates. So let's write the reaction rate. That is the next step. R equal to Kf times those two concentrations minus the other concentration divided by the K equilibrium. These should be the same name that you gave in your component list, that which we created under Aspen properties. Should be exactly be the same name. Okay. Anybody has any trouble, please raise your hand. So the only three equations we have written so far are these three equations. Once you are done with that, now we need to write the model equations. So how we should write the model equations are, this is how you write the model equations. So I'll go back to the slide very quickly and I'll talk a little bit about that. Okay, so this is how you declare any of the variables C, and then whatever is the component name you gave it, and so we go for that. Now next thing is the mass balance equations. We just simply use a for loop, and then we use if, else if, and all of that, or end if or end for, to loop through all the components, right? And we would need to link this information with respect to the port variable. Remember that in Aspen what we just declared was the input port and output port. So we have to basically say this particular variable, how they are linked to those input and the output ports, right? So we need to write everything in terms of that. So like for example, if I am actually doing a flow rate feed A dot F, that means that is the molar flow rate in feed A. Okay. So this is the standard way of structuring. So this is how you write it. So feed A, so that is basically meaning is that whatever is coming through port name feed A dot F, that is the flow rate, times feed A dot Z, this is the mole fraction, plus feed B dot F times feed B dot Z, this is the mole fraction of the components in that through feed B, minus the product here the same way, PROD dot F and dot Z, minus R times V, right? So this is how each of these variables are actually being declared. And then we keep writing these for all of this. So see the declaration. So in Aspen, if for a declaration you use two equal sign. If you use a single equal sign, that's an equation. This is a declaration. This is basically saying if I is equal to, so this basically means is equal to, but in Aspen, a equal sign does not mean it is equal to. It will treat it as an equation, but this is not an equation. We are just basically considering this as a type. So we are saying if this is this, then, so for any character or any other things, that is how you actually declare it. So let's keep doing it. If, else, elif, and else, and then end if. So this is how it should be written. I will go back to the actual code so that you can see how this is being done here. Okay, so we now need to write the material balance equation as it is being shown here. Let's write these equations. Okay. It's not a problem, no. No, for as so this is the fundamental difference with MATLAB and Aspen. Aspen doesn't care. You can write anything anywhere, it will actually arrange it for you. When it sends to the solver, it will arrange and move things around. Do not worry about it. MATLAB has got those exactly this way it should be done. This is not needed for Aspen. Yeah, if you want to write it on the right hand side 0, that's write it. It's up to you, whichever way. Sorry?
After this one.
Oh, you are already here. Okay. So basically, if you go to the model, go to the custom modeling. So if you want to see the model, so go to the custom modeling. No, above it, the custom modeling. Yeah, the custom model here. Yeah. So click it. Click on the models. Yeah, and you will see CSTF, and then click this guy. This will open up. Yeah. You're good. Okay. Okay.
Reactant, I mean, reactant in forward reaction, we
Uh-huh.
have put two different statements. But for the reverse reaction, there is only one.
Yeah, this was actually not needed. We just showed you to how to write it because this is exactly the same, right?
Yes, sir.
Yeah, it basically, if you show the forward one, you could have both for the forward one, and then this one. So it basically showing how to write it. You can write it in many different ways. Yeah.
And what does this in stands for? I mean, I as in a part of component list. Is that so?
It is actually what it means is that if it is, as I was saying, that equal to means for Aspen is an equation, but this is an assignment. So if it is saying that if I is equal to this, because this is we are saying I in the component list. So component list is an array.
Right.
So it is basically, it's a character that it is comparing it with. It is not a variable, it is a character. That is why we put an assignment here, right? Okay, all right. Yeah, that's all right. Yeah, say okay. Yes. And then you say import using import Aspen properties. This is the file that we shared with you, right? That's the one you are opening? Or?
Yes, yes, same file.
Yeah, so go to the folder where that file you placed.
Desktop. See the path control. IIP, user IIP download, desktop file.
Yeah, it's probably already looking for it. So go to Aspen custom model, no, it's already there. Oh, so you want to put it here. Okay. No, that is fine. Okay, and now you go to there. Going to this, can I see? So it's already looking for it here. No, where is the file you wanted to open? Yes. No, so go to the location where it is.
Why are we having this internal logic? Because we have the same formula for all the components.
Right. So what I was saying is this gives you a flexibility to show that how you write it. So the purpose of this is structured is like that. You can also use a plus minus sign, and just only two notations would have been even fine because one is for the feed and the product. But this basically show you that if it is not the same component, this is how you write it. Yeah. Feel free to play with the way we declare it. Okay, all right, and then once you have that, the next equation that which we write here is that I guess everybody has looking into the file that we gave you here. The other thing is that summation of mole fraction, so it is 1 equal to summation of mole fraction. Here we are using the sigma operator, right? The sigma operator is basically summing it up over here over all components. So it is saying sigma is equal to product dot z over all component list. So this is what it does. And then we have to relate the concentration to density. This is the one last equation that we need to work on. We are saying Ci is equal to rho times Yi. So we will say C component list is equal to rho mole times product Z times component list. So this is the equation and this is how we write it, right? And I will show you those equations are here. Sorry. Those equations are here, right? If you have opened the file here, that sigma equation is here and this rho equation is here. So remember, for Aspen it doesn't matter which side is left, which side is right. So I can write it in any way. I can write this as 1 minus sigma equal to 0, many different way. And this is not the only way to declaring it. It basically showing you how to use a for loop, how to use an if else loop, but you are free to declare it many other ways. So it does not matter actually how you actually do any of these. Okay. Once you have that, there is only one thing that we are doing here is a properties call. So this is the density call that which we are making. So I'll go back to the file here again. So the property call is there are a number of property calls are there. So remember that Aspen properties file that you called there, and it is embedded there. So anytime you make a properties call, it will go to that file and then go to Aspen properties and dig out the numbers or do the calculation for you. So it's not a simple properties thing that you are thinking, but it is basically behind the scene. There are actually all the equations that are there in Aspen properties that it will be actually pulling from there. So it requires you the Aspen plus engine as well as Aspen properties. So I know some of the machines that was giving the error that I was saying that I am not sure why it is. But behind the scene, it is the Aspen engine actually that calls those files behind the scene for doing the calculations. So what you really need to see here is if you want to see that what are the inbuilt properties there, so please go to libraries, procedures. So in your ACM file, please click libraries and then click procedures. Under there you will see a number of them. So all of those that are listed under there are all your properties call. And out of those properties call, the only one that we are getting it is rho density molar liquid. So it is basically saying what properties call it is making. So it is basically saying I am actually calculating specific liquid molar density. I also can give you analytic derivative if you want for it. And this is the call that it is making. What is the library? This is a DLL. This is originally written in Fortran. It is inputs are temperature, pressure, mole fraction, and output it is giving you as dense mole. So that is why we declared this as dense mole. So from here you will be able to really find this type, right? So see how we are doing it. So you see that we said call rho dense mole liquid TP product G component list. So this sequence, this array. So please everybody, if you can look at me, like if I know you have our model here, but this is something I want to for everybody to be clear here, please. This argument is not arbitrary. what comes first in this argument, like whether the T will come first or the P will come first or this will come first, it depends upon the actual procedure call. So see this because here we are just calling density. For your model you may be calling like viscosity, you may be calling diffusivity, other parameters. So how will you make this? So what it is doing, it is saying call rho mole. So that basically means is that it is returning, this is actually listing the variable output name. So this is the output name, and then this is the property call, this is the property call, and then this argument here has to follow a structure. So what it is, why T is first? How do I know whether T would be first or P would be first? For understanding this, you have to go to this subroutine. So rho dense mole liquid. So I'm going there now. So if I go here, and I go to the libraries and I say procedures, and here are all the properties that are there. So there is a bunch of properties that you can do. So what is the one that we are calling? Rho dense mole liquid, right? So this is the one, right? So for coming here, libraries, modeler, procedures, and then this guy, the diamond icon. Once it is there, double click onto that. See, it tells you everything. So this rho mole, that which we are doing, this is my name that I gave. It must follow this sequence. So here the temperature comes first. So that is what I am saying it as T. So what Aspen will do is, whatever comes in the first argument, it will interpret, oh, this is temperature. So this must follow this sequence. Temperature, so whatever is in the variable here, it will assign that part. This variable name is yours, but whenever you separate it by a comma, it will interpret that as the first input argument. So this is the first input argument, this is the second input argument, and this is the third input argument that it is looking for. Is this thing clear? This is the strength of Aspen actually, these properties. So ensure that we know how to make the properties call. You will be making all kind of excess enthalpy calls, all the other calls that you need, and this is exactly the structure and for you how to look into. For everything that you see there, you double click, it will show you what is the output, what it is expecting in its argument name.
But here input the coding, first input comes temperature.
Right.
So where the T means the T will associated with temperature.
Right, right.
So T means pressure is okay.
Yeah.
Third production element in
yeah.
the argument.
Yeah.
But here third here more.
Yeah. This is just to ensure we are on the same page. This is your variable name. You name it anything. Instead of T, I can just write my name in it. Instead of pressure P, you can just put whatever variable name it wants it. It does not care. This is your variable name. So whatever you do it by comma, this is what it is looking for. So what is the first thing? This is whatever is the first one before the comma, that it will assign to this guy. The second one it will assign to this guy. So it is a comma delimited. So that comma basically tells you that this is the end of this first argument. Is this clear to everybody, right? How we declare these things? Okay. Okay, so once it is done, and we are kind of a little bit running out of time, but that's okay. I'll just say, somehow I cannot figure it out. Okay, so once you are done with that, I just said this actually. Then the next thing for any of these will be compiling the code. When you compile the code, that tells you so far we are very happy. I'm just writing it. I'm not sure if I made a typo or I forgot something. When you compile the code, that is when Aspen will tell you if something is wrong or something is not working fine. So I will show you, this is the most important part here. So let's see this. I come here and come to the code. So this is already done, but I can compile. So right click here. So right click on this model platform, and then there is an option called compile. So do click on that one, please. What you are really looking for is, so if I do compile, it says compilation completed, 0 error, 0 warnings. But if I mess up something, and I will show you that, and you will see that what it will be complaining. Like for example, I actually mess up here, I say 1, 2, right? I just type it some arbitrary one, right? And I just come here and I'll say compile it. It immediately says there are compilation error. What it is the thing? Then it is coming exactly the one where I made the mistake, right? I say compilation list 1, 2. It is basically saying error at position 32. Property compilation list 2, 1, 2 does not exist in model CSTR. So it's a typo that I made here, okay? I could make other things here, like for example, I can say, well, I made some typo here times 3 times whatever 4. Let's say I made some typo here, right? And I say do some compilation. It immediately find out and it tells me, no, these are not right, and it goes there actually immediately, tells you. So this compilation is one of the important things. This is first checks you, when you do compile, it first checks it for syntaxing error. That's the first step. Syntaxing error, it works. That does not mean your compilation is fine. It also do a structural analysis. This is the most important one. So after you do the compilation, what you are really looking for is this green button here. Not button, that's green indication. If you see the green, it is happy. It is basically saying, yep, your number of equations and number of variables are the same. There is no issue with respect to this. However, I will show you a case where it will be actually is not happy about it. So what it basically does is, let's say I go to this equation and I comment it out. Okay? See what happens now. If I comment it out and I say compile, you see, it actually say red, and you bring your cursor here, it will say under by 1. That basically means you have one equation less. So it is immediately finds out that you have one equation less, and this is the equation that I write here. If you do the other way around, let's say I write something called, I just copy this equation and I make it something. I basically say 2 times, maybe I will say 2 times, just arbitrary something. I say rho mole times this equal to 0, right? Just a wrong equation I just write. You see that, did you see how it flipped now? That it was under, but now I wrote and one more equation. If you see it, it now said you are over by 1. Okay, so it keeps looking into this. Then the other thing which we'll be talking about, the notorious one, is the wrench icon, which will probably, we are running out of time, I will show you next day. The wrench icon basically is, I just cannot figure it out what you have done. That's the most tough one, right? So that one will talk about this. But nevertheless, once you have this, if you have compiled it, and I have compiled it successfully, so then the next step is basically to run it. Please do run. For running it, you just need to click it here. So click run, and if you have that model that I shared with you, it will actually run. See how, I'm not sure how you are declaring it, but let's check this. It should be conc_mol. Yeah, take the actual model, because we'll probably not have too much of time, but need to check it out. So once you have that and you run this steady state, there are two things I wanted to show that it will show up. So this, as I said, the simulation message is important here. If I run here, it said the run has completed, so it is happy about it. And it is saying solving steady state. It is giving you solving group size, whatever it is, whatever is the number here, and all of those things. If you want
Sir,
more,
I handed down.
yes, please. Yeah, go ahead, please. Do we need to? Yeah, please go ahead. We need to click here. Yeah.
Yes, sir. Yes, sir. So regarding the concentration, so the variables that were there. So these variables were already predefined in the software, or these are the ones that we have created it, sir. So we have defined it now.
Yeah. So I'm sharing. Okay. Are I not sharing so far, or? Sorry. Okay. Are you able to see my screen?
Yes, sir.
So if you see here, what we really did was that we took the variable types, right? So if you see here, so you talked about concentration mole, right? So see, it was already created for us. So if you go to the variable type and you see here the concentration mole, it is already created by Aspen. You see there are so many types, it is already created. So if you double click on that, and then it will tell you that what it is looking for. So it is basically saying, I'm taking the unit of kilomole per meter cube, that is my unit, this is my default value, lower is this bound and upper is this bound, and this is actually a molar concentration.
Okay, sir.
Okay.
So we don't need to define anything now, sir, explicitly. So these are already predefined by the Aspen, so that we are taking it for writing the code.
That is true, unless there is a type that you need to create yourself. Like if you, this is a very big list, right? You see how big of a list it is, right, on this side, variable types.
Yes.
But other than these, if you come across that there is a variable type that is not here, you can create the variable type yourself, or you can declare that as a no type.
Okay, sir.
Okay. Already. Okay, so one thing I would like to say, we are actually running out of time. I will, this CSTR is the only thing I wanted to show, and the other things we'll see how much time we have. But one thing I wanted to show you, that if you want to see more message, so this one is a very good case that it converts, but you can create a case where it will not convert. That time you like to see more messages here. The way to see more messages here is that you right click on the simulation message window, then you say solver reporting level, and there you can say very high or maximum. If you do it maximum and it is not converging, it will actually print too many things for you. So you have to keep adjusting it. By default it is, so maximum is this. The other thing which I would like to mention here is that, which you did not get a chance to talk about, you need to go to the solver option, and here go to the nonlinear solver. So once again, for troubleshooting, we'll talk more about in Aspen AdSim, but here the same platform, right? So solver option, nonlinear solver, under the diagnostics, print like 5 highest variable steps and highest residuals. This will give you which variables and which equation it has trouble in solving. Okay, and from there you will be able to figure it out. So now it will probably still go fine, but you see it actually printed lot more information than what it printed before. You see previously it just printed only this part, now it actually printed lot more. It is basically saying I am solving the group 1. In the group 1 what equation I am using, what variables are actually in this group, current value is this, this is the residual, this is the derivative of that one. Then it is saying okay, what are the equations in group 2, that is saying K equilibrium, and then other variables is group 3, every other variables are actually as part of that. And then it is saying residual tolerance is this, relative tolerance is this, absolute tolerance is this, how many iterations it took to converge, and all of this information that is actually it is using. So if you run into trouble, print those, at least look into the residuals and variables, and then increase the solver message. To be honest with you, if you do the maximum level and if it is not converging, it will be printing you like thousands of pages of messages, because the solver has got a lot of diagnostics inside. You most cases don't want to see that. But if it is really a difficult problem that you are running with, this is the way to look into. Okay. What I'm actually going to do now is that I will skip a lot of these things here. What I would like to mention here is for everybody who is participating that I will share this with you. Basically try it like doing the building the flow sheet. Like once you have created the model, building the flow sheet is simply drag and drop into that that overall window, and then you connect the streams here. So this presentation is done in a way you should be able to follow along, and this is how you put the streams. When you click the streams, it will tell you which streams you want to connect. You connect all of those streams. So this is how we connected it, and then once you connected it, it will say this is not squared. Then these are the things that which I said, and we'll be recreating some of the trouble tomorrow, day after tomorrow, to show you how it goes. Then we had 13 degrees of freedom. We needed to specify all of those things over here, and then we say how to fix these variables like free to fixed or whatever. These are the feed compositions that we are fixing it, and then we fix all these variables, and then you can specify what variables is what type. Then degrees of freedom icon, as I said, that we have already run it, and then you see all the results. The only thing I wanted to show here is, before we go, once you have run the code, you are interested in looking into the results, right? You can double click on this thing to see the results. So I can see the results. It will give you the results for all. So you see there are two types. So free, 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 that means it is calculating those for you. And fixed means what we have specified. So those are numbers are there. If you only want to look at the subcategory of variables, you double click and you go for the forms. These ones has got only all variables, but you can create other variables that you want to do it. Like you can say I want to explore what variables are there. So this is as part of that. I also wanted to show that if you have a variable from here and then you want to do it as, let's say I have all variables table here, and I want to create any of these in form of a, you can create a plot. So this is the icon over here. You can create a plot or variables. We will be spending more time on Aspen add seam so that you will see this. We will be going more slowly and look into this. But if for creating this you come to the table and you give it a name. So I say whatever, right, and I say this may be a table, like you can do a profile, plot, table, whatever. I can say create a table. It create a table for me. Now what I can simply do is that if I am interested in finding the results for one of these, like for example this guy, I can just simply drag and drop. See, I came here and then I will drop it over here. That's it. You can create, drag and drop. So I just come here and say I want to see this variable. I just bring it and drop it over here, and it creates the table for me. And I can, once I'm done from here, I can run the code. See, these values are 0.15 and 0.34, and I know if I'm changing these inputs, these will change. So maybe flow rate instead of 1, I make it like 1.5 or whatever, right? And you can rerun the thing and you can go back and see the results here, right? So where is my thing goes? So remember, anytime I create any of these things, it will show up under the custom modeling. So if I go into the custom modeling, it will show you anything that you created and give it a name. So it is probably hiding behind the scene somewhere. Let me see where it is. Yeah, it's here. So you see that these numbers actually got changed, right? So you can drag and drop and put these windows. So all of those things are possible. Okay. So the folder that I shared with you, I did know that I would not have time. This is like the material that I have almost will take a 1 day if I really want to work with you all. But what I wanted to tell you that what I shared with you has got a file that has got, shows you a lot of things, including DAE, how to have the DAE and how to create the DAE. This is for plug flow reactor. Then we also show that how to code these things in the DAE, and then I also have an example here of, this is the plug flow reactor problem, and then we have the dynamics here. I will also say, if you really want to do the dynamics, if you see our book here, you have, actually this is the previous version of our book, like latest versions. I know many of the colleges follow that our design book here. This book has got one chapter completely dedicated on dynamic simulation. So this is the standard design book in the senior design. Many schools actually teaches it, but you can follow this one here to look into. One last thing, when you have a time derivative, to tell Aspen that it is a time derivative, you actually use a dollar sign. So when you have a dollar sign like this, it tells Aspen that it is a time derivative. That's it. Nothing else, no fancy thing you need to do. Just simply say it is a dollar sign. And I have a few things running about the dynamic simulation and all of those things. We'll spend some more time on these. Another thing which I mentioned about the snapshot management, like this option, like you can create a snapshot. Anytime you get a successful solution, you can save the snapshot. By default, Aspen will save the snap like here. These options are here. This is an important one. I just quickly wanted to show you, like this is this overall places. Whenever you try to do any of these systems here, I will always say that generally keep creating a really good snapshot for overall systems that you want to have. So for now, if I actually just simply come here and I say take a snapshot and I give it a name, I say good, it will create a snapshot for me. So it is there. You see that this is the snapshot it takes for me. So next time I come and want to load this snapshot, I just come here and I will say copy value, or I say rewind value, and I say okay, it will take me to exactly that place. So I could have multiple instances of this one. Aspen has got this create option. It's saying when do you like me to create that snapshot? We're saying after steady state, after initialization and all of that. These are probably too many options, so you create too many files for these ones. So if you have a gigantic file, your file size will keep increasing and increasing. I will say decide when you really want to take a snapshot. Like if I run this code, I actually uncheck all of those things. I take snapshot myself by saying whenever I am happy, I will take a snapshot. I don't want Aspen to take default snapshots for me, but it is up to you. The problem with Aspen is that this snapshot that it is taking, when you say save, this snapshot will be saved along with the file. So one fine morning, you will find out that you have a file 100 MB, but you say, why my code is not so large? Why it is 100 MB? This is because of the snapshots actually. Then you somehow you need to open it, and then you can delete those snapshots and save it, and it will be gone. So that's the problem. This is the main difference between Aspen and gproms. Gproms saves all the files in all the snapshot in a separate file. Okay. I think this is the main thing that I wanted to tell you. Do see my dynamic simulation here. The solver options I will go as part of Aspen AdSim. This was the tolerances that which we talked about. These are the solvers. We'll spend more time. These are the integrator options. We already discussed all the integrator options that it has here. And then the plotting, I just showed you one plotting, but in AdSim I will show you this other plotting. And we'll talk about also running the task there. So again, please look into these, and also these convergence issues. These are suggestions that what to avoid, how to code, and all of those things. And there is also something I wanted to highlight, but we do not have time here, is the degeneracy that basically tells you there is no solution that would exist for certain formulations. And you just need to be careful about this, because it's not a problem for Aspen, it is because how I coded it that it is the equations are degenerate. Okay. Scaling is important thing. Again, whatever scaling you wanted to have, you need to have a equation scaling and variable scaling, and we can discuss about that sometimes in the future if we have run a time permitting here. So what I will suggest here is that if you have any time here, please do look into which one you said? Can I see it here? Yeah.
There is nothing at the bottom. Right between those U and all.
Oh, okay. Oh, okay. So okay. So first of all, so these whatever you are seeing it here is the, you say view, and these are toolbars.
Draw
so
toolbars.
No, these are the standard toolbars. Hold on.
It's not coming out.
No, hold on. Model libraries, you come
Okay,
here.
model library. That's
Yes. So okay. Anything else? Anybody has? Sorry. So you go to the view and say model libraries. The view and model libraries. Yeah, now it shows. Any other last question here, please? Yes. Yes.
Compilation.
Oh, this is the fun one actually. When it shows you this one, that the range icon, that is simply telling you that somewhere something is wrong for you to really figure it out, that where it is. So we have to sit with the code and see where it is. Like this does not tell you where is the trouble. Did you take mine one and did it, or you modified anything here?
Before that, I write my question. After that, it's not compiling. Then I copy paste your code.
When you have this range icon, that is basically tells you that, but this particular is something got started here, and you have done already done the component list and all of that. Let me quickly check this, and your component list has got the default. No, so this is the thing. So remember, the name should match here. So this is, we are calling it as MEOH. It must be whatever is your methanol, CH3OH. Which one is that one? I cannot, yeah, methanol. So this is as MEOH. We're done actually.
Quick break.
Yeah, let's do that actually.
So that another.
Yeah, so that you can actually start off. Yes, absolutely. Yeah, so if anybody wants to stay and have any questions, I'll be here. Otherwise, let's go for a tea break, right?
So we'll have quick tea break for 15 minutes and we'll come back for the next tutorial. Okay, that is the MATLAB basics. Okay. We'll meet again at 4:25. Good. Okay then, call the driver. ఆఫ్ ఓకే ఆఫ్ చేసాను ఆఫ్ చేసాను ఓ నేను మాట్లాడేటప్పుడు ఓకే కదా ఆన్లో ఉందా ఓకే హైటా So welcome everyone. So I will continue the tutorial 1 that is regarding the MATLAB basics. So I will switch from MATLAB window to the presentation. Okay, we have commands that are present in both the cases. Okay, you can either follow this or follow my MATLAB screen. Okay. So as I mentioned, all of you create one folder on desktop where you can have MATLAB separately and Aspen separately. Okay, just create one folder for the MATLAB on the desktop. Maybe inside your name or any specific name that you would like to represent. So MATLAB is actually a advanced calculator, okay, where we can perform several types of operations, mathematical operations especially. Before going into the solving the problems or writing the codes, I will just show you how to execute the commands and what is the MATLAB environment. And if you see the first point, it is written as getting started with the MATLAB. If you would like to go through multiple comments and what are the starting points of understanding and learning the MATLAB, you can go through this link. Okay, this will take you to the MathWorks website. So the abbreviation of this MATLAB is nothing but Matrix Laboratory, and it is designed to work with numbers one at a time and designed to operate primarily one whole matrices and also the arrays. That means set of numbers we will be working with. We will see how to build the matrices, arrays, okay, and also how to solve the equations that we need, the parameters that we would like to find out. So if you open your MATLAB, everyone click on the MATLAB here. Okay, you see the window symbol, right? There you can type MATLAB and open the software. And we can see what are the variables written and what is the output that we are trying to calculate. So what about this? What is written over here? So G might drive IIPE. Okay, you see this thing now. What is this? So that is the address, okay, address of the folder. If you save your MATLAB file, okay, you will see the address where you are storing the information. That is important, okay, because you don't want to lose the information that you are trying to calculate, okay. So now moving forward, so if you would like to assign one value to the parameter, okay, it could be any parameter. Here we have x equals to 10, okay, and also the y equals to 20. So all of you opened your MATLAB, right? You can just simply click x equals to 10, okay, and click enter. So this here you can see once you click enter, right, it would assign and it will store the value 10 in the variable x. Okay, if you see the workspace, in the workspace also you can see the value of x. Now you can use x whenever you want the value of 10. Okay, that is the value that we assigned for the x. Okay, similarly you can assign the same value to the 20 to the y. Okay, you can see in the workspace that x and y values are stored. So now we will do one simple mathematical operation, that is z is equals to x plus y. So now you have x, y and the z values. So z is nothing but the summation of both x and y. Okay, this is a simple calculation that we are using the MATLAB command window to execute it. Good, everybody on the same page, right? Fine. Then try this. We'll do few more mathematical operations. So we have x value as 10, okay, and we are trying to calculate cos of x, and we are assigning that value to the a. So now you can go and check in the workspace what is the value of the a, okay. So similarly we can try another trigonometric operation, that is a tan of y. So we have given the y value as 20, and we are trying to calculate the tan of y. Okay, you can see the answer, that is 2.2372. So now everybody try b equals to x by y semicolon. So what is the answer you got? So what is the answer you got? What is the answer you got? Yes, answer is correct. Okay, however, answer you should check in the workspace. Okay, if you are using the semicolon, you don't see the answer in the command window. Okay, however, the value is stored in the b. So if we are typing b equals to x by y, it is 0.5. Okay, if I am giving the same value with the semicolon, okay, you don't see the answer here, however it will be stored. Okay, we can go to the workspace and check those values. So if you want to see all the different values we created, okay, you can click the arrow mark, the one which is denoting the top, okay, the up arrow mark. If you click on that, you can see what are the various commands you have given so far in the command window. Okay, you can go one by one, and if you would like to go to the previous history, what are the various commands that you executed in the command window, those you can see here. X equals to 10, y equals to 20, and z equals to x plus y, and a equals to cos x tan y. Okay, and if you click enter, again you will be executing the same command in the command window. This is one easiest way of going back to the previous command. Okay, in MATLAB we have different data types. Okay, so if we are assigning one single number, for example, given as a equals to 2, okay, that is a data type. The data type is called the scalar. Okay, and if we are assigning multiple numbers, okay, multiple numbers like list of numbers, if we are assigning that, we represent it as array. Okay, the list of numbers. Arrays again we can classify into vectors and the matrix. Okay, what is matrix? We have studied the matrix in our mathematics, right? Yes, if we are having the two-dimensional array, that is rows and the columns, okay, as example that is given over here, C equals to 1 2 0 3 4 7, that is one of the example for the matrix, okay, which contains either one or more rows, okay, or one or more columns. Then coming to the vector, okay, vector is a list of numbers, either the rows or the columns, which is in a 1D, okay, one dimensional array. That is, it could be either row vector or the column vector. So I will show what is the difference between this row vector and the column vector and how to execute them. Okay, if you want only the row vector, how to get that, and if you want only the column vector, how to find that. Okay, so array is nothing but a collection of elements of the same data, okay, same type of data. So you can try executing these values in your command windows as it is. Try once by giving a equals to 2, capital A is equals to 2, that is your scalar. Okay, that is followed by vector. Try vector, that is B. So if you are dividing the numbers by commas, okay, that means you will print, MATLAB will print that as a row vector. Okay, if you are dividing the numbers by semicolons, when there is a semicolon, MATLAB reads that as going to the next row. Okay, so that is the difference in creating the row vector and the column vector. So commas will move to the next element in the column. Okay, the semicolon will move to the second row. So you can combine both the row vector and the column vector, the commas and the semicolons that we used, and build one matrix. Okay, the matrix that is shown here, that is the C. C can be created by separating the elements by using the commas and also the semicolons. Good. Anyone is having difficulty in executing this? So if you lost the answer, you can go to the workspace and check what is the answer. Okay, if you want to go back to the previous command, click that arrow mark which is showing upwards. Okay, that is like a history of the comments. So if you are using the same name, okay, the same alphabet again, okay, it will overwrite. So the previous value will be overwritten by the new value if you are using the same alphabet. So this is the row vector. If instead of instead of commas, if you are just leaving with the space also, it will take it as the same row. Okay, it won't go to the second row unless you use the semicolon. Either you can use the space here or the comma, and when you would like to move to the next row, you can use the semicolon here. Okay, that will create one matrix. Now we will move to the next step, that is creating a array. Okay, so to create an array with elements in a single row, separate the elements either with a comma or the space, that is what we have just now shown. Okay, and that is the row vector. So you can try this also, this example, to create x. X is a row vector. Try with both the spaces and also the commas. So we are doing this exercise to be more familiar with the MATLAB environment, okay, for the tutorial that we will be doing tomorrow. Okay, now moving to this building the matrix. So if you don't want to use both commas and the semicolons, okay, you can go with the spaces and also use the enter button to move to the next line. Okay, in the same command window, that will also print the matrix. Okay, you can try this. Okay, this is another way of doing it. So what is the application of learning this matrix, building the matrix in the context of this course? Okay. Anyone else? Any other answers? So in for example, if you take the adsorption equilibrium calculations, okay, we will get the data in at different points, different pressures and the different temperatures. We will get the adsorption uptake. Okay, if you list out everything, you will get one matrix. Okay, that matrix we will use, the data that is present in the matrix, okay, that information we will use to fit the adsorption isotherm models, okay, to estimate the parameters. Okay, so this will help you in understanding how to build this matrix and how to use this information in the fitting. Okay, that we will go through in coming class. So MATLAB also have a set of functions, okay, such as the three functions I have shown here. One is zeros. So the zeros that, if we are using this command zeros of 3 comma 1, okay, that creates 3 rows of zeros and 1 column. Okay, the answer that is shown over here, you can try these 3 commands and check what is the answer for this, and that is followed by ones. If we would like to create only the elements or the matrix or column vector that is contains only the 1, okay, then we can use this particular function called ONES. Okay, then we have RAND. What is that meant? Random values. Okay, you want some random matrix contains random values, you can use this function RAND, okay, and how many number of rows you want and how many number of columns you want. So each of you will get different values if you are using this RAND. It depends, we can change also. If yeah, you can try help RAND, that will show you any other changes we can make. Yeah. All of you got the answers, right? Same, not the same answer. For RAND you don't get the same answer. Okay, so now we will move to the next step. So if we are adding the same value, okay, the value that is 20 to the matrix, your matrix, okay, this is a scalar addition. We have a 20, that is the same constant value that will be added to the each element that is present in the matrix. So previously we created a matrix that contains 1, 2, 3, 4, 5, 6 and 7, 8, 9 elements. Okay, when we are adding this 20, it will be added to the elements that are present in the matrix. So what is the second command? What it is doing? No, transpose. Okay, it will change the columns and the rows. Okay, that is the transpose. The single quote we can use to change the rows and the columns. So don't delete the values that you are producing. Okay, I will show how to erase them also. Okay, now moving forward, we will see the standard matrix multiplication. Here we multiplied the z, that is a scalar, okay, with inverse of a. Okay, MATLAB is very efficient. It could do the inverse if you are using this command inv of a. Okay, it does the job of inverse. Just create a first and calculate the inverse of a. Okay, then multiply it with z. Okay, if you haven't created the z value before, okay, it will show the error. So z has been defined. Okay, if I define this value of a, that is 1 comma 2 comma 5, 2 comma 4 comma 6 and 7 comma 8 comma 10, this will create the a. So INV of a, that is the inverse matrix. Okay, this is the inverse matrix. When we multiply the z with inverse of a, okay, you can either use inverse of a or ANS. Okay, when we are not assigning the number to any variable, okay, it will take ANS. Okay, ANS as a variable, it will store in that. If you are not defining any alphabet, it will store that in the ANS. So this is the answer. You can cross check that with the given in the slides. So all of you got the answer right? Good. Okay then. So there is another interesting property here that we were discussing, that is concatenation. Okay, how to merging the two matrix. If we are using A is a matrix, okay, and the small a, if we are using the commas, okay, it will merge the both the matrix horizontally. Try this. You created matrix A, right? Small a. Or else if you don't have small a or the matrix, you can create one matrix first and use this command comma in between those two matrix. So this command is useful if you are getting your experimental data from two different setups. Okay, if you would like to merge both of them when the variables are same, okay, then this command is useful for you for the column matrix or the horizontally or the vertically. So if you want to merge them vertically, you can use the semicolon in between. Okay. So you can see the order of the matrix, how that is changing in the workspace. If you double click on the workspace, you can see the order of the matrix. So I had this thing, okay. In the workspace you can see at the bottom, if you take your cursor to the variable, okay, at the bottom you can see what is the order. That is a 3 by 3. So x, we can see this is a 3 by 6. Okay, we have 3 rows and the 6 columns. If you want to see all the elements, you can double click on this variable, it will take you to the table. Okay, what are the values that we are assigned to this variable called x. Similarly, we can check the y also. So, order of the y is 6 by 3. Okay, we have 6 rows and also the 3 columns. Good, right? Okay. So, array indexing is a very interesting property. If you would like to extract any one element from the list of data points we have, okay, for example, I have a 3 by 3 matrix and I would like to extract one element of it, okay. So, by using this array indexing, we can pick that element. So, first create one matrix, matrix that is A is equals to random rand of 3 comma 3, that will create you one matrix. Okay. However, I want to extract the second row second element. Okay. This command A of A bracket open, okay, that is 2 comma 2 and bracket close, that will extract you the element in the second row second column. Once you extract, you can assign it to the another variable, that is also possible. Okay, if you take some z or y is equals to a of 2 comma 2, okay, the value that is extracted from the matrix A and it will store in the z, okay, or else you can see if you type ANS, okay, that value will be printed, whatever the value that is extracted. It is clear, right? You can try another index also, instead of 2 comma 3 you can try something else and check whether it is working or not. You can create another matrix and check whether it is extracting the value correctly or not. Okay. So, we will move to the next topic. So, you see there is this colon that is in between 1 comma 3. Okay. Instead of one element, if we would like to extract the entire row or entire column, okay, then we can use this notation, that is A of 2 comma 1 is to 3. That means from the column 1 to 3. So, the elements that are present from the column 1 to 3 will be extracted, that is present in the second row. So, the 2 is representing the row number, okay, and 1 is to 3, that is representing the columns, the elements that are present from the column 1 to the column 3. So, if you again go back to your matrix A and if you cross check what is the second row, it is supposed to extract entire the second row. So, if you don't know how many number of elements that are present in the second row, okay, you can simply use the column notation there, okay, that will extract the entire second row. But if you are very specific about picking few numbers, okay, if you would like to find out some error in your data, okay, where you know what is the column numbers and what is the row numbers of the data points, okay, that is also possible to extract. Or you would like to generate some data points, okay, the data points within the period of some 20 or period of 1 or any number 1 is to 20 is to 100, the columns that we are using, okay, that will create the series of the numbers with the interval of the 20. If you are not representing the interval, okay, it will take the default as 1. You can try 1 is to 20 in your command window and check what it is giving. So what is the answer you got? How many numbers you got? It created a vector, right? Row vector. How many elements are there? You can check the order in your workspace. Okay, we have 20 elements which contains 20 columns and only one row. Okay, so let's do this. I have 5, okay, 5 is to 20 if I try to execute this command, okay, what it will do, it will add by default 1 to the 5 until it reaches the 20. So what is the answer for this? Can you see what is the command I am executing here? What is the answer you will get? Try. 20 is to 5. Yeah, null or empty matrix, okay, because it will always by default try to increase the number and reach to the next level, okay. However, if we add 1, it will go to the 21, okay. If you want to go from 20 to 5 in descending order, okay, you need to use -1 instead, okay, that will take from 20 to the 5, okay, it will use -1, it will add every time -1 to the next value till it reaches the 5. So I sent you one Excel file to everyone. I sent you one Excel file with the name of CO2N2. So download that Excel file and keep it in the folder that you created on the desktop. All of you got that Excel file, right? Okay. So we will see how to load the information, the experimental information that we obtain from the studies into the MATLAB. So at the top here, okay, below this toolbar, here you can see up one level button, right? You can click on that. So first thing is you need to go to the address to the folder that we created, okay, where the files of Excel file is saved. So once you open that, here either you can copy or type this command. Okay, the command is data is equals to xls read co2n2 dot xlsx. This xllx may change if you are saving it in different different format. It could be, if it is a CSV, you need to mention the CSV. So A1 to C67 representing how many number of elements that are starting from column A in the Excel file to the column C. So if I go back to that Excel file, okay, I will open this Excel file and show you. So this is the Excel file which we got. This contains the CO2 and N2 adsorption isotherm data points, okay, at temperature T and the pressure. What is the adsorption uptake? Okay, this is experimental information. This is taken from the literature. Okay, similarly we have, this is for the CO2 and the sheet 2 contains the N2. Okay, let's concentrate on the CO2 first. So always you need to mention how many number of rows are present from the A1 to the C226. You need to represent in the command window here. So once you type this command, okay, if you click enter, then in the workspace you can see the data that is loaded, the experimental data that is uploaded into the MATLAB. So if you would like to cross check, you can click on the data. Okay, the data that is in the Excel sheet that can be uploaded here. So we will be using this information for the calculations. Okay, that is from the experimental studies. Okay, so this is the command I used. Once you need to go to that folder, the MATLAB folder that you created, right, where the Excel file is stored, then use this command to load the data. So anyone having the difficulty in loading, let us know. Okay, we will help you. So this is important step. This is the starting point in estimation of the parameters. Once we load the experimental data, okay, we'll use that information to estimate those parameters by fitting.
Function what we usually want, but here it is like R to be 650, so I should put this name only.
Wait, yeah, it's great.
How do I specify the folder?
One thing, you can open the folder. Yeah, open. Where did you create your folder and okay, then open. No, it will open the MATLAB figures.
This is the file.
Yes. That's okay. I guess you are in the folder. Now try that command.
CO2 underscore sheet 1 A1 to C227. Is that correct?
Yes. That means number of rows, whatever the rows.
But involving the expression x read.
I guess you are not in the folder still. Okay. Okay, this will take you to the folder, select folder. Okay, see, the thing is, still this command will work if you are giving the address of that folder. Okay, we are directly calling the file name, but we are not giving the address. Okay, now if you click enter, it will load because we are in the same folder. Yeah, still it is showing the issue. However, we were in the same folder with the same name. Invalid expression, there could be some.
X, yes.
So there is a single quote missed. Okay, yeah, now you can see your isotherm information there. Is it loaded? So everyone, if you are not in the same folder, at the top you can see the address, right? Just give the address before the Excel file. That means the CO2n2.excel, Excel SX. Okay, if you are providing the address of the folder also, it will load. You don't need to be in that same folder. Yeah, so this will take you to the folder where you saved your Excel file. Are you in the same folder?
Right click on
it's not working, huh?
you can.
Okay, it is in
Desktop.
Okay. Kishore, right?
Yes.
Once you select this, you saved the Excel file in that, right?
Yes, sir. Under the MATLAB section.
This section we selected, or okay, your name we selected. Okay. It should display if everything goes. Yeah. Okay, that's how it will. Yes. Arey, you were asking.
I have chosen this one. This one is a file, and I have to
load it. Now it loaded, na data. Where is the data? Excel SX, not XC. No, no. Someone might have using this round off thing. to the 4 decimals. You can go for use this long comment. Okay, that will take you to the decimals as much you want.
And one more thing,
Yeah.
like here when I was making the matrix, I actually used this like this 5s, 3, 3, but it says unrecognized 5s. You remember you were mentioning zeros?
Zeros is there, but 5s is not there. Zeros is there, ones is there,
Zeros and ones only is
ones are there. Yeah, there aren't any 5s.
Okay, okay.
Yeah. So all of you would able to load the data, right? Okay. So if you see, we can extract that only the temperature separately, the pressure separately, and adsorption amount. Can you do that? From the basics that we learned, can we classify the temperatures, pressures, and the adsorption amount? If you open the Excel file which I sent, okay, which is the first column? Temperature is the first column, right? Okay. Assign all the columns, okay, the columns that are present in the data. So we loaded this Excel file into the data. Okay, now the data is a big matrix. The matrix contains 3 columns, 227 rows. Okay, the first column is temperature. Can you extract only the temperature first? So the T is equals to, the data is our matrix. So what we will do, we want the first column and all the rows. What is the symbol for all the rows? Colon. Okay, we will use the colon and we want the first column. Okay, this column represents all the rows. Okay, when we use the comma, it will go to the second the index that represents the columns. We want only the first column. That first column is for the temperature. Okay. So all the temperature values that are present in the Excel file, the data now is assigned to the T. Okay. T means the temperature. Similarly, we can assign the pressure and also the adsorption amount. So these are the values of the pressure which is in the bars, I guess. We need to multiply with 10 power 5 to make it into the pascals, and we will take adsorption amount that is in Q. Okay. So this is how we will extract the information obtained from the experiments. Okay, the data is a matrix that we loaded. P is the pressure, T is the temperature, and Q is the adsorption amount. So it is clear for everyone, right? First you need to load an Excel file, then that is followed by column operations to assign that information to the variables that we will be using. Okay. Yeah. It is simple. When you are using the column symbol, right? That means everything, every element that is present in that column. Okay, all the rows. So MATLAB we can use to plot it. Okay, some plots or some comments here you can see. Okay, these commands, the first command representing generating the information for x, okay, with the space from linspace 0 to 4 pi, and that is followed by y is equals to, y is our dependent variable, okay, x is an independent variable. So once you have x values, y will be calculated as a cos of x, okay. Then the symbol, the command plot of x comma y, okay, that will create you that plot. You can try these commands in your command window, all these commands you can try. So x label gives the label to the x axis and y label gives the label to the y axis, and if you are using this command called title, okay, that can you can write the title of your plot. Try all these commands together. If you are using that semicolon at the end, okay, you don't see the result of x and y, but you can see the result in the workspace. Yes. D or T? T, right? Yeah.
Okay.
Where is your comment? Yeah, you assigned all the rows for the T, but you didn't assign which column.
Okay.
Okay, that is the error actually, but before that you might have, this is TEM. Okay, that could be the reason.
Should I put 1?
Yeah.
Oh, now.
Yeah. So.
So what does this 4 cross pi means?
4 multiplied by pi, 3.14 is
So
right?
this will take till 0 into.
Yeah, that's it. Interval, it's like 0 to the endpoints. Yeah, hardly 10 minutes it will take. I will finish it up.
How it is selecting the interval, like the difference between these two?
You can check whether it is uniform or non-uniform.
But it's random.
Yeah, that is the answer. You can make uniform interval also. See, you didn't execute the command called plot xy. That is the important command you missed. Okay, that means you are not telling MATLAB to plot x versus y, but you are asking MATLAB to give the title to the plot. That's why it is just showing the title on empty graph. It's okay, I will share the slides, you can try the same comments. You got the plot, right? So if you execute the same commands, you will get the plot. So till now we were running multiple commands on the command window, okay, but where there is this another window called script window, that is where the code is written, okay. So if you go to the MATLAB environment, at the top you can see the layout, right? You can click on the layout and go to the either default, okay. If you go to the default, so you will see this variables, and also you will see which folder you are in, and also the command window goes down here at the bottom, and we have a workspace, okay. So if you click on plus symbol, the new, okay, it will give us multiple options, either script, live script, function, okay, and also the class, test class. Let's worry about the script first. You can click on the script, okay. Here it will create the script window. I will minimize this variables. Okay, this is the editor, okay. This is where we write our code to execute or to solve the equations, okay. In case if you want all the windows, you can again go back to the default option, okay. You can see the workspace, command window, and also the folder which you are in, okay, while you are writing the script here. So I will write one simple script. All of you also you could able to open the editor, right? Good. You can go to the plus symbol and click on the script. It will open the editor. If you want this same environment, you can go to the default option in the layout, okay. That will show all these 4 windows together. So I will just show you one small script file. We will write one. If you are using this percentile symbol in the script window, that means the we are writing a comments. Okay, comments are important in the very large codes. Okay, when we are giving multiple commands, okay, we should understand what is the command that we are giving and what is the problem we are solving. So during the time, these comments will be very useful. So if you are putting this percentile symbol, that we are telling MATLAB that this is not a command, this is a statement. Okay, this will store as a statement. So what type of problem we are solving? For example, here I will write this is a area. So area and volume of the sphere. Okay, that is my first statement. Then what I will do? First, I will assign the radius. Okay, sphere radius. Sphere radius is r equals to 1. Okay, then that is followed by A, that is the area that we are trying to calculate, that is nothing but 4 pi r square. Okay, we will represent this with 4 multiplied by pi. Multiplication is the symbol we use, that is multiplied by r square. Okay, so then coming to the volume, you can give it as V, capital V. Okay, that is 4 by 3 multiplied by 3.14 r cube. Okay, this will calculate. This is a small script that will give us area and volume of the sphere. So now once this is done, you can go to the editor. Okay, editor button is at the top. And this green symbol, right, this is a play symbol that we see, or the run. Okay, you can click on that. So it will ask us whether the script file has a name or not. Okay, you have created a folder, so you can go and store your files, the script files, in the same folder. You can name this as area and volume of sphere. Okay, and we can click save. Okay, it will save, and run the script file. If you go back to the workspace, okay, my area is 12.5564 and volume is, okay, as I mentioned, we can clear all the commands that we had run. It created a lot of information, right? That information can be cleared. Either you can go here to this box, the downwards arrow, and we can clear the command window. And similarly here we can go and clear the workspace. Okay, now if you run, okay, in the workspace we can see only the variables that are created from the script file, that is area and the volume. Okay, the area is 5664 and the volume is 4.1888, and there is one information, the independent variable that we provided, that is the radius r. Okay, this is called the script file. Okay, in MATLAB we generally write the script files, okay, to solve the problems. The outputs will be reported in the workspace. Okay, it is clear, right? So I will conclude this session at this point. Okay, I will continue this in the tomorrow's tutorial. Okay, start from this point. I will teach you few other basics, and also I will show you how to estimate the parameters for the adsorption isotherm models. That is very important in the modeling of either breakthrough curves or the pressure swing adsorptions. That is the first important step. Okay. Are there any doubts, or do you have any questions? So I will share the slides. If you want, you can practice. Okay. If you want, you can stay for some time and also practice. That is also fine. So are there any comments from online participants?
అది కాదు సార్ క్లోజ్ చేయండి సార్.
Okay everyone, thank you. So we will meet tomorrow morning, okay, as per the schedule.